Hello there and welcome to Life Beyond Seen, where the deepest questions tend to arrive quietly. The way water fills a dark space, slowly, without announcement, until you realise it has been there all along. Tonight we're going somewhere that most people have never heard of, and fewer still have ever seen. Not because it is hidden behind a locked door or buried in a classified file somewhere, but because it sits at the bottom of an ocean, beneath thousands of meters of cold, pressing, lightless water in a place so remote and so hostile that even the scientists who study it most closely have learned, sometimes the hard way, to keep a respectful distance from certain parts of it. We are going to the Romanche Trench. Say that name slowly and it already sounds like something that belongs to another world. Romanche. It has a softness to it that does not quite match what it actually is, which is one of the deepest and least explored underwater chasms on the entire planet. A wound in the floor of the equatorial Atlantic so vast and so strange in its behaviour that it has quietly frustrated, baffled and occasionally defeated some of the most experienced oceanographic teams on Earth. Not because they were careless, not because the technology was not good enough, but because the Romanche has a particular way of making things go wrong. And it does so in ways that even experienced researchers find difficult to fully predict. There is something almost philosophical about a place like this. We live in an era where satellites can read the temperature of a wheat field from orbit, where submersibles have reached the deepest point of the Mariana Trench, where the surface of Mars has been photographed in higher resolution than some parts of our own ocean floor. And yet here, in the Atlantic, not in some distant corner of the Pacific, not beneath the Arctic ice, but in the equatorial Atlantic, a place we might reasonably expect to know fairly well by now, there is a trench that remains, in large portions, genuinely unexplored. A place where instruments go in and do not always come back out, where the water itself behaves in ways that complicate every plan made on the surface, where the scientific community has, over time, developed a kind of quiet institutional caution about certain zones, not born of superstition, but born of experience and the very practical calculation of what things cost when they disappear into the dark. That is what we're going to explore tonight. Not a mystery in the dramatic sense, not a conspiracy, not a legend. Something more interesting than that. A real scientific puzzle, built from real physics, real geography, real engineering failures, and real questions that oceanographers are still working to answer. The kind of puzzle that does not announce itself loudly but sits at the edge of our understanding, patient and deep, waiting. Before we go any further, I want to pause for just a moment and ask you something simple. Where are you listening from tonight? Are you somewhere warm, settled in with something soft nearby, the kind of evening that asks nothing of you? Or are you somewhere cooler, the kind of night where the window has gone dark early and the room feels a little smaller and more comfortable for it? And what time is it where you are? Midnight perhaps, or somewhere in that long quiet stretch between 10 and 2, when the day finally loosens its grip and the mind starts to wander toward bigger, stranger things. Whatever the hour, whatever the temperature, I am glad you are here. Because this is the kind of story that rewards a slow pace. It does not need to be rushed. It has been waiting at the bottom of the Atlantic for a very long time, and it can wait a little longer while you get comfortable. If this is the kind of quiet, curious journey you enjoy, I would be genuinely grateful if you took a moment to like this video or subscribe to Life Beyond Seen. It is a small thing that makes a real difference in helping this channel reach other people who might be looking for exactly this, a slow, careful, thoughtful place to spend an hour. No pressure, no urgency, just a gentle ask, the way the ocean asks nothing of you except your attention, now. Let us talk about the Romanche Trench. The first thing to understand is that the Romanche is not simply deep. Many places in the ocean are deep. What makes the Romanche unusual is the combination of where it sits, how it was formed, what happens inside it, and what that means for anyone who tries to study it seriously. It occupies a position on the floor of the Atlantic Ocean right along the equator, which sounds almost too neat to be true, like something a geography teacher would draw on a chalkboard to make a point. But there it is, straddling the equatorial line in the central Atlantic, running roughly east to west for several hundred kilometres, reaching depths that in some measurements exceed 7,500 metres. That is deeper than Mount Everest is tall. And unlike Everest, which at least has the courtesy to be visible from a distance, the Romanche sits beneath a column of ocean so thick and so dark that no sunlight has ever touched its floor. Not once. Not in any geological age. Not ever. It was carved into existence by the same slow violence that shapes all oceanic trenches, the movement of tectonic plates, the grinding and pulling of the Earth's crust along fault lines that have been active for tens of millions of years. The Romanche sits along what geologists call a transform fault zone, a place where two plates do not simply move apart or toward each other, but slide past one another horizontally, like two enormous pieces of stone being dragged in opposite directions by forces we can barely imagine. This kind of movement creates fracture zones, and the Romanche is one of the largest of these along the mid-Atlantic ridge, the great underwater mountain chain that runs down the centre of the Atlantic like a spine. The trench is, in a sense, a gap in that spine, a deep transverse cut across the ridge, and it is this position that gives it a role in the ocean circulation that goes far beyond its size. But we're getting a little ahead of ourselves, and that is one of the pleasures of a story like this. There is always more underneath. What matters in this opening moment is simply the scale of the thing and the strangeness of its obscurity. The Romanche Trench is not a small feature. It is not a minor footnote in the atlas of the ocean floor. It is one of the deepest places in the Atlantic Ocean. It plays a significant role in the movement of deep water across the planet, and it sits in a part of the ocean that human ships have been crossing for centuries. Portuguese sailors passed over it in the age of exploration without knowing it was there. Slave ships crossed those waters. Merchant vessels, warships, ocean liners, container ships, all of them moved across the surface of an ocean that concealed somewhere beneath their keels this vast and restless gash in the Earth's crust. And for most of the history of human seafaring, no one knew it existed at all. Even after it was discovered, even after its depths were first measured, even after the scientific community understood what it was and where it was, the Romanche remained, and in many ways remains today, one of the least studied deep ocean environments on the planet. Not the least known. People know it exists. It appears on oceanographic maps. Papers have been written about it. Expeditions have visited its vicinity. But there is a difference between knowing a place exists and actually understanding it, and the gap between those two things in the case of the Romanche is still surprisingly wide. This is the question that sits at the centre of tonight's story. Why, with all the technology we have, with all the interest in deep ocean science, with all the growing urgency around understanding how our oceans function and how they are changing, why does the Romanche Trench still have zones that scientists effectively avoid? Why do experienced researchers, people who have spent careers studying the deep ocean, speak about certain parts of this trench with a kind of careful, measured reluctance? Not fear in any dramatic sense, something quieter than that. A professional wariness. A recognition that this particular place has a way of complicating things that goes beyond the ordinary difficulties of deep ocean work. The answer, as we will explore tonight, is not simple. It is not one thing. It is a layering of physical conditions, engineering realities, financial pressures, geological instability, and a kind of accumulated institutional memory built from lost instruments, failed deployments, and expeditions that returned with less data than they hoped, and more questions than they started with. It is a story about the limits of technology when technology meets a truly hostile environment. It is a story about the hidden mechanics of the ocean and what happens when the deep water of the Antarctic pushes through a narrow equatorial gap and creates conditions that no instrument was quite designed for. And it is, in a quieter way, a story about how science actually works in practice, how funding shapes knowledge, how logistics shape ambition, and how some of the most important places on Earth remain understudied simply because reaching them properly is genuinely, stubbornly expensive and hard. There is also something else here, something a little harder to name. The Romanche has a way of making the ocean feel large again. We have grown comfortable, perhaps, with the idea that the deep sea has been mapped, that the major features are known, that the work of discovery is largely finished, and what remains is the work of detail and confirmation. The Romanche quietly disagrees. It sits there in the equatorial Atlantic, not particularly far from anywhere, not hidden behind ice or locked inside a polar night, and it still holds things we do not know. It still behaves in ways we cannot entirely predict. It still swallows instruments without apology. And that in itself is worth sitting with for a while. So tonight we're going to take this slowly. We will start at the surface, with geography and history, and we will work our way down, layer by layer, into the physical conditions, the strange behaviour of the water, the documented failures, the biology, the geology, the politics, and finally the growing recognition that understanding the Romanche is not just a matter of scientific curiosity, but something that matters for our understanding of how the entire Atlantic Ocean circulates, and through that, how the climate of the planet behaves. We will separate what is known from what is suspected, what is confirmed from what remains genuinely open. We will not pretend the mysteries are greater than they are, and we will not pretend the answers are simpler than they are. We will just go slowly, the way the deep water itself moves, steadily, patiently, in the dark. And to understand why the Romanche is still so difficult to study, why certain zones still give experienced oceanographers pause, we first have to understand what it actually is and where it actually sits, because the geography of this trench is not just a backdrop to the story. It is part of the reason the story exists at all. The Atlantic Ocean, if you look at it from above, has a kind of symmetry that is almost architectural. Two continents facing each other across a body of water that widens as you move south, narrows slightly at the equator, and then opens again into the broad southern reaches toward Antarctica. It looks, from a certain angle, like the two land masses were once pressed together and then slowly pulled apart, which is in fact almost exactly what happened. And running down the centre of this ocean, roughly equidistant from the coasts on either side, is one of the longest mountain ranges on Earth, a feature so large and so continuous that it is almost impossible to picture properly. The Mid-Atlantic Ridge, a chain of underwater mountains, rift valleys and volcanic formations that stretches from the Arctic Ocean in the north all the way down to the subantarctic waters in the south. More than 16,000 kilometres of geological structure, most of it completely invisible from the surface, most of it never seen by human eyes. It is along this ridge, at the point where it crosses the equator, that the Romanche Trench sits. And to understand why the trench exists at all, it helps to understand what the Mid-Atlantic Ridge actually is. The ridge marks the boundary between two great tectonic plates, the North American and South American plates on the western side, and the Eurasian and African plates on the eastern side. These plates are moving, not quickly, not in any way you would notice in a human lifetime, but measurably, steadily, over geological time. They are pulling apart from each other along the ridge, and as they separate, magma wells up from below, cools, and forms new ocean floor. The Atlantic Ocean is, in this sense, still growing. It widens by a few centimetres every year, the way a crack in old pavement slowly spreads across seasons. But the ridge does not run as a single clean line. It is interrupted, offset, broken into segments by features called transform faults. These are fracture zones where sections of the ridge are displaced sideways relative to each other, where the plates slide past one another horizontally rather than simply pulling apart. And it is one of these transform faults, one of the largest and most dramatic, that carved the Romanche Trench into existence. The Romanche fracture zone is an east-west gash in the ocean floor that cuts across the mid-Atlantic ridge right at the equator, offsetting the ridge by nearly 900 kilometres. That is not a small displacement. That is a geological feature of considerable scale, and the trench that runs along part of it reflects that scale directly. The Romanche Trench itself extends for roughly 900 kilometres in length, which is already a remarkable distance to sustain at depth, but it is the depth that tends to stop people when they first encounter the numbers. The trench reaches approximately 7,800 metres at its deepest measured point, depending on the survey and the methodology used. Some estimates place certain zones slightly deeper, though the exact figure has been revised over the years as measurement technology has improved and as different expeditions have returned with different data. What is not in dispute is the general scale. Nearly 8 kilometres from the ocean surface to the floor of the trench. That is deeper than the cruising altitude of many commercial aircraft, measured in the opposite direction. For comparison, the Mariana Trench in the Pacific, which holds the record as the deepest known point on Earth, reaches approximately 11 kilometres at its deepest. The Romanche, then, is not the deepest trench on the planet, but this comparison, while useful for scale, also partly explains why the Romanche has historically received less attention than it deserves. The Mariana captured the imagination of explorers, scientists, and the public in a way that the Romanche never quite did. The deepest point on Earth is a compelling title. It draws funding, expeditions, documentaries, and public interest. The fourth or fifth deepest trench in the Atlantic, sitting quietly at the equator, does not carry quite the same narrative weight, even if its scientific importance is in some respects considerably greater. To put the depth in terms that feel a little more tangible, consider that if you placed Mount Everest inside the Romanche Trench, the summit would still be more than 2.5 kilometres below the ocean surface. The water column above the floor of the trench is not simply a long distance. It is a long distance filled with increasing pressure, decreasing light, and shifting temperature gradients that change the physical properties of everything inside them. The weight of that water column creates pressures at the bottom of the trench that are roughly 770 times the atmospheric pressure at sea level. Materials that behave normally at the surface behave differently under that kind of force. Gases compress. Metals can deform slowly over time. Electronics become unpredictable. Seals and joints that hold perfectly well in a laboratory test can fail in ways that are difficult to anticipate and nearly impossible to diagnose after the fact. The trench is located at approximately 0 degrees latitude, which is to say directly on the equator, roughly midway between the coast of Brazil to the west and the coast of West Africa to the east. The nearest land masses of any significance are the small equatorial islands of São Pedro and São Paulo, a tiny Brazilian archipelago that sits almost directly above the fracture zone, and the island of St Helena, that remote British territory in the South Atlantic, several hundred kilometres to the southeast. These are not busy parts of the ocean. There are no nearby ports of any consequence. There are no research stations within easy reach. The equatorial Atlantic at this longitude is, in practical terms, genuinely remote, not in the way that the Arctic or the deep Pacific are remote, but remote in the sense that getting there requires a substantial ocean crossing from any direction, and getting there with the kind of heavy, specialised equipment that deep ocean research demands requires either a very well-equipped research vessel or a logistical arrangement that most institutions find difficult to justify. This remoteness is worth dwelling on for a moment, because it is easy to look at a map and see the Romanche sitting in the middle of the Atlantic and think, well, it is not that far from anything. Ships cross the Atlantic regularly. The equator is not an unusual place to be, but there is a significant difference between crossing the Atlantic and conducting deep ocean research in the middle of it. A container ship passing over the Romanche Trench needs nothing from the ocean floor below it. A research vessel attempting to lower instruments to nearly 8 kilometres of depth needs to remain stationary, or nearly so, in open equatorial waters for extended periods of time, while managing cables, moorings, remotely operated vehicles and acoustic communication systems in conditions that are rarely cooperative. The equatorial Atlantic is not known for calm, predictable weather. It is not known for still water. And the Romanche, as we will come to understand, has its own particular set of conditions that make even basic instrument deployment considerably more complicated than it might appear on paper. What makes the location of the Romanche especially significant, beyond its depth and its length, is that it sits at a point where the underwater topography of the Atlantic creates a kind of gateway. The mid-Atlantic ridge is not just a mountain range, it is also a barrier. It runs down the centre of the Atlantic and effectively divides the deep ocean floor into two separate basins, the western basin on the American side and the eastern basin on the African side. Deep water does not flow easily over the ridge because the ridge rises high enough in most places to block the movement of the coldest, densest water along the ocean floor, but the Romanche fracture zone cuts through the ridge at depth. It provides a passage, one of the few places in the entire Atlantic where deep water can move from one basin to the other without having to rise significantly. And the water that uses this passage is not just any water. It is Antarctic bottom water, some of the coldest, densest, most oxygen-rich water in the entire ocean, formed near the edges of Antarctica and sinking to the ocean floor before beginning a slow, deep journey northward through the Atlantic. The Romanche Trench is one of the principal doors through which that water passes on its way into the eastern Atlantic basin. This is the detail that elevates the Romanche from an interesting geological feature to something genuinely important for understanding how the ocean works. But it is also the detail that makes studying it so difficult, because the passing water does not move quietly or predictably through the trench. It creates conditions inside the fracture zone that are, by the standards of deep ocean research, unusually turbulent, unusually complex, and unusually hostile to the equipment that scientists depend on. That, however, is a story for a little later in the evening. For now, it is worth staying with the geography a little longer, because the relative obscurity of the Romanche compared to other deep ocean features is itself an interesting puzzle. It is not as if the Atlantic is poorly studied in general. The North Atlantic in particular has been the subject of intensive oceanographic research for well over a century, partly because of its proximity to major research institutions in Europe and North America, partly because of its role in climate regulation, and partly because of its historical importance for navigation and commerce. The Atlantic is, in many ways, the most studied ocean on Earth, and yet sitting almost exactly in the middle of it, right on the equator, is one of the deepest and most geologically significant features in the entire ocean, and it remains, by almost any measure, significantly underexplored. Part of the reason is simply the geography of scientific infrastructure. The major oceanographic institutions that have historically driven deep-sea research are located in the North Atlantic region, in the United States, in the United Kingdom, in Germany, in France. Their research vessels are based in northern ports. Their funding cycles and scientific priorities have tended to favour the North Atlantic, the Arctic and the Pacific, where either the scientific questions feel most pressing or the logistics are most manageable. The equatorial Atlantic sits at an awkward distance from all of these centres, not impossibly far, but far enough that a research expedition to the Romanche requires a significant commitment of ship time, fuel and personnel that competing priorities have repeatedly displaced. There is also the matter of what deep ocean scientists call the Pacific bias. The deepest trenches, the most dramatic subduction zones, the most active volcanic features are disproportionately located in the Pacific. The Pacific has captured the imagination of deep-sea researchers in a way that has shaped funding priorities and institutional attention for decades. The Mariana Trench, the Tonga Trench, the Philippine Trench, these are the features that tend to appear in textbooks and documentaries and grant applications. The Romanche, for all its scale, has not quite broken through into the same level of popular scientific consciousness. It is known to specialists. It is understood to be important. But it has not, at least until relatively recently, attracted the kind of sustained, well-funded research attention that its significance arguably warrants. And so it sits there at the equator, in the middle of the Atlantic, nearly 8 kilometers deep, carrying some of the most important deep water on the planet through one of the few passages in the mid-ocean ridge, and doing so largely without an audience. Not because no one cares, not because the science is uninteresting, but because the combination of remoteness, logistical difficulty, competing priorities, and the particular hostility of its physical conditions has kept it, decade after decade, in a kind of quiet shadow. The depth and the geography, then, are only the beginning of the story. They tell us where the trench is and how large it is and why it matters in principle. But they do not yet explain the specific reluctance, that careful, measured wariness that experienced researchers bring to certain parts of the trench. To understand that, we have to go back further in time, to the earliest moments when human beings first became aware that something extraordinary lay beneath those equatorial waters, and to the long, slow, interrupted history of trying to understand what it was. The story of how humanity came to know about the Romanche Trench is not a story of sudden discovery. It does not have a clean, dramatic moment, no triumphant flag planted, no single expedition that pulled back the curtain and revealed everything at once. It is instead a story of gradual accumulation, of slow and often interrupted understanding, of knowledge pieced together across decades by people who were frequently not even sure what they were measuring. And that slowness, that long gap between first awareness and real comprehension, is itself part of why the trench remains so incompletely understood today. To go back to the beginning, we have to go back to a time when the ocean floor was almost entirely theoretical. For most of human history, the deep sea was simply the deep sea. People knew it was there. They knew it was dark and cold and presumably very deep. But the actual topography of the seafloor, the mountains and valleys and fractures and plains that lay beneath thousands of meters of water, was entirely beyond reach. The tools did not exist to measure it with any precision, and the conceptual framework for understanding what might be down there had barely begun to develop. The ocean bottom was, in a very practical sense, imaginary. That began to change in the 19th century, and it changed primarily because of one thing: the laying of telegraph cables. The ambition to connect continents by underwater cable forced engineers and scientists to think seriously about the seafloor for the first time. You cannot lay a cable across the Atlantic without knowing something about what you are laying it on. And so, in the middle decades of the 19th century, there was a surge of practical interest in ocean depth measurement, in what sailors called sounding. The technique was not complicated in principle. You lowered a weighted line over the side of a ship, let it sink until it touched the bottom, and then measured how much line you had paid out. In practice, it was slow, laborious, and prone to error, particularly in deep water where currents could carry the line at an angle and produce readings that were difficult to interpret. But it worked well enough to begin sketching a rough picture of the ocean floor. It was during this period of early systematic sounding that the first hints of something unusual in the equatorial Atlantic began to emerge. Ships crossing the Atlantic along equatorial routes occasionally recorded depth that seemed surprisingly large. Measurements that suggested the seafloor dropped away more steeply and more deeply than the surrounding region would predict. These readings were noted, filed away, and in many cases not immediately followed up, partly because the technology of the time made it genuinely difficult to be certain about very deep measurements, and partly because there was simply so much ocean to account for that no single anomalous reading commanded urgent attention. The ocean in those early decades of systematic study was full of surprises, and not every surprise could be chased down at once. The expedition that gave the trench its name arrived in 1883. The French naval vessel HMS Romanche, on a mission to observe the transit of Venus from the island of St. Paul in the equatorial Atlantic, passed through the region and conducted a series of soundings that confirmed the presence of an unusually deep feature in the fracture zone along the equatorial ridge. The ship was not primarily an oceanographic vessel. Its mission was astronomical. But the practice of taking soundings while at sea was standard procedure for naval expeditions of the time, and the depth readings that the Romanche recorded were striking enough to be noted in the expedition's records, and eventually to attach the ship's name to the feature itself. It is worth pausing on that detail for a moment, because there is something quietly telling about it. The trench that would turn out to be one of the deepest and most significant geological features in the Atlantic was first formally documented almost as a side note by a ship that was really there to look at a planet passing in front of the sun. The ocean's greatest depths, in the early days of exploration, had a tendency to be stumbled upon rather than sought out. Scientists were not yet asking the specific questions that would make the Romanche Trench obviously worth investigating. They were gathering general data, building a rough picture, and the trench appeared in that picture as an interesting depth anomaly, noted, named, and then largely set aside. The decades that followed were not entirely silent on the subject of the Romanche, but they were not exactly busy either. The late 19th and early 20th centuries were a period of expanding oceanographic ambition. The HMS Challenger expedition of the 1870s had transformed the study of the deep ocean and demonstrated that systematic scientific investigation of the seafloor was both possible and enormously productive. In the decades after Challenger, a number of national expeditions followed, and the general outlines of the Atlantic seafloor began to come into sharper focus. The Romanche fracture zone was recognised as a significant feature, and occasional expeditions passed through the region and added data points to the growing picture. But the trench itself, as a specific object of sustained scientific inquiry, remained peripheral. Part of the reason was simply technological. The wire sounding methods of the 19th century were adequate for establishing that deep features existed, but they were far too slow and imprecise for anything like detailed mapping. A ship could spend days taking soundings across a small area and still produce only a very rough sketch of the topography below. To understand the Romanche Trench with any real precision, scientists would need tools that did not yet exist. The development of echo sounding in the early 20th century changed this fundamentally. By sending a pulse of sound downward and measuring the time it took to return from the seafloor, ships could take depth measurements quickly, continuously, and with far greater reliability than wire sounding allowed. Echo sounding made it possible for the first time to build genuinely detailed maps of the ocean floor, and it transformed what oceanographers could know about features like the Romanche. But technology alone does not drive science. Funding does. Institutional priority does. The particular interests and questions of the scientific community at any given moment do. And through the first half of the 20th century, the deep equatorial Atlantic was not where the most pressing oceanographic questions seemed to lie. The North Atlantic was the focus of intense research because of its role in transatlantic shipping, its relevance to weather patterns affecting Europe and North America, and its proximity to the institutions doing the research. The Pacific was drawing attention because of its extraordinary geological activity and the sheer drama of its deep trenches. The Romanche sat in a kind of institutional middle ground, known, acknowledged, periodically visited, but never quite elevated to the level of sustained priority. The mid-20th century brought new tools and new urgency to ocean science. The development of sonar technology during and after the Second World War had profound consequences for oceanography. Military investment in understanding the acoustic properties of the ocean produced instruments and techniques that scientists quickly adapted for research purposes. The post-war decades saw an explosion of systematic ocean floor mapping, driven in part by the Cold War logic that understanding the ocean was strategically important, and in part by the genuine scientific excitement of a period in which the theory of plate tectonics was beginning to reshape the entire way that geologists and oceanographers thought about the Earth. It was during this period that the mid-Atlantic ridge was mapped in detail, and with it the fracture zones that cut through it. the Romanche fracture zone came into sharper focus as an important structural feature, a transform fault along which two sections of the ocean floor were sliding past each other, creating the deep trench that bore the old French ship's name. The significance of the trench as a passage for deep water circulation was beginning to be appreciated, and yet, even as the broader geological context became clearer, actual expeditions into the trench itself remained infrequent. The mapping was improving. The theoretical understanding was advancing, but the physical reality of the trench, the sediments on its floor, the water moving through it, the organisms that might live in it, remained largely unknown. There is something almost paradoxical about this situation, and it is worth sitting with it for a moment. Here was a feature that scientists were increasingly confident was important, a deep passage through the mid-ocean ridge carrying cold Antarctic water into the eastern Atlantic basin, a major structural element of the transform fault system, a potential repository of sedimentary records stretching back millions of years. All of this was understood in outline, and yet the expeditions needed to study it in detail kept not happening, or happened only briefly with limited equipment, without the sustained follow-up that would have been needed to build a real body of knowledge. Some of this reluctance was logistical, as it always is in deep ocean research. Equatorial Atlantic expeditions are expensive and difficult to mount from northern ports. Ship time is finite and fiercely competed for. The trench is deep enough that standard oceanographic equipment is tested near its limits, and the conditions inside the fracture zone, as researchers who did venture there began to discover, were more challenging than the simple depth figures suggested. But some of it was also a kind of institutional inertia, the quiet, self-reinforcing logic by which understudied places tend to remain understudied. If there are few published papers on a feature, it is harder to make the case for funding a new expedition to study it. If the existing data are sparse, the scientific community does not have a clear picture of what questions most urgently need answering, and if the feature has not captured public or institutional imagination in the way that, say, the Mariana Trench has, the competitive disadvantage in grant applications is real. The Romanche existed in this loop for much of the 20th century, known enough to be taken seriously, unknown enough that taking it seriously always seemed slightly less urgent than the alternatives. The expeditions that did reach the trench over the course of the 20th century were often remarkable in what they found, even if their findings did not immediately translate into the kind of sustained follow-up attention the results might have warranted. Sediment cores taken from the trench floor revealed records of deep ocean circulation and climate going back millions of years. Water sampling confirmed the presence of Antarctic bottom water moving through the fracture zone and provided early data on its temperature, salinity and oxygen content. Biological sampling, where it occurred, turned up organisms adapted to the extreme conditions of the deep trench environment. Each of these findings pointed toward the same conclusion. The Romanche was scientifically significant in multiple overlapping ways, and the existing data were nowhere near sufficient to understand it properly. And yet the expeditions remained sporadic, the follow-up incomplete, the picture frustratingly partial. By the late 20th century, the technology available for deep ocean research had advanced dramatically. Remotely operated vehicles, autonomous underwater vehicles, long-term mooring systems capable of recording data over months or years, high-resolution multi-beam sonar systems that could produce detailed three-dimensional maps of the seafloor. All of these tools had transformed what was theoretically possible in a place like the Romanche. The question was no longer simply whether the technology existed to study the trench properly. The question was whether the combination of funding, scientific priority, logistical willingness, and institutional appetite could be assembled in sufficient quantity and at the right moment to make it happen. And the answer, as the 20th century gave way to the 21st, remained frustratingly incomplete. What the long discovery history of the Romanche Trench reveals, when you trace it from those early 19th century soundings through to the present day, is not a story of neglect exactly. Scientists have known about the trench. They have studied it in pieces across time. They have understood its importance in principle for decades. But it is a story of persistent incompleteness, of a feature that has always been just slightly beyond the edge of what sustained scientific attention could reach. Each period brought new tools and new understanding, but also new reasons why the full study kept being deferred. The trench has been visited, but it has never quite been known. And the gap between those two things, between having been there and actually understanding what is there, is where the real story of the Romanche begins. Because the history of discovery is only one dimension of the puzzle. The other dimension, the one that has shaped the specific, careful wariness that researchers bring to certain parts of the trench today, is not about when people went there or how often. It is about what they encountered when they did. The physical conditions inside the Romanche fracture zone are not simply extreme in the generic sense that all deep ocean environments are extreme. They are extreme in specific, unusual, and in some respects genuinely surprising ways. Ways that have tested equipment, frustrated deployments, and produced a body of hard experience that any scientist planning an expedition to the trench has to reckon with carefully before committing instruments or personnel. And it is to those conditions, to the particular character of what waits inside the trench, that the story turns next. To understand what makes the Romanche Trench genuinely unusual as a physical environment, it helps to start not with the depth itself, but with the location. Most of the world's deepest ocean trenches sit in the Pacific, far from the equator, in cold, relatively stable water columns, where the variables, while extreme, are at least consistent in their extremity. The Mariana Trench, the Tonga Trench, the Philippine Trench, these are places where the conditions are brutal but, in a certain sense, predictable. Cold, dark, crushing, still. The Romanche is none of those things in quite the same way because the Romanche does not simply sit in the deep ocean. It cuts across the equator, and the equator in oceanographic terms is not a neutral line. It is a boundary, a zone of collision, a place where the physics of ocean circulation become genuinely complicated in ways that compound every other challenge the trench already presents. The pressure inside the Romanche is, of course, enormous. At its greatest depths, approaching 7.5 kilometers below the surface, the water column above exerts something in the range of 750 times the atmospheric pressure experienced at sea level. This is the kind of figure that is easy to state and difficult to truly picture. One way to approach it is to think about what it means for a hollow metal sphere, the sort used in scientific instrument housings. At those pressures, materials that feel solid and reliable at the surface behave differently. Metals compress, flex, and fatigue in ways that are difficult to model perfectly. Seals that hold without question at 100 meters become potential failure points at 7 kilometers. Electronic components rated for deep ocean use are tested against these conditions in laboratory tanks. But a laboratory tank is not the same as the actual environment, and the difference, when it matters, tends to matter completely. The engineering required to send instruments to the floor of the Romanche is not simply a scaled-up version of shallow water oceanography. It is a different discipline, with different tolerances, different failure modes, and a much smaller margin for error. The temperature at the bottom of the trench is near freezing, typically somewhere between 1 and 2 degrees Celsius, and in some parts of the fracture zone, even colder than that. This is not unusual for abyssal depths in general, but the Romanche sits at the equator, where the surface water above it is warm, sometimes reaching 28 or 29 degrees Celsius. The result is a water column of extraordinary thermal contrast. Cold, dense water pooled in the depths of the trench, warm water sitting at the surface thousands of meters above, and a complex layered structure in between. For equipment being lowered through this column, the thermal transitions create mechanical stress. Materials expand and contract as they pass through different temperature zones. Lubricants that perform well in warm surface conditions may behave unpredictably as temperatures drop toward freezing. Syntactic foam, the material used to provide buoyancy to deep ocean instruments, is rated for specific pressure and temperature combinations, and the passage through such an extreme thermal gradient is not something that can be entirely accounted for in advance. But the pressure and the cold, significant as they are arguably not the most unusual features of the Romanche environment. What truly sets the trench apart from other deep ocean environments is what happens inside it with water movement. The Romanche fracture zone is one of the most important pathways for Antarctic bottom water in the entire Atlantic Ocean. Antarctic bottom water is exactly what its name suggests. Extremely cold, extremely dense water that forms near Antarctica, sinks to the ocean floor, and spreads northward along the bottom of the Atlantic basin. It is among the densest water in the world ocean, and its movement is a fundamental driver of global deep ocean circulation. Without it, the deep Atlantic would be a very different place, thermally, chemically, and biologically. The problem, from the perspective of anyone trying to deploy instruments inside the Romanche, is that this massive flow of Antarctic bottom water does not simply slide smoothly through this fracture zone like water through a pipe. The geometry of the trench is complicated. The fracture zone is not a simple straight channel. It has ridges, sills, basins, and narrowings that force the water to accelerate, compress, and change direction as it moves through. When a large volume of dense cold water is forced through a constricted passage, the result is turbulence. Not the mild, predictable turbulence of a river moving around a gentle bend, but something more energetic and less orderly. The flow can develop internal waves, which are oscillations within the water column itself, invisible at the surface but capable of moving enormous amounts of water up and down over vertical distances of hundreds of meters. These internal waves can travel through the water column for long distances, and inside a confined space like the Romanche, they can interact with the topography in ways that produce highly localized, highly variable current patterns. What this means in practical terms is that the current environment inside the Romanche is not uniform. In one part of the trench, the water might be moving relatively slowly, and instruments deployed there might sit quietly on their moorings for months without incident. In another part, only a few kilometers away, the current might be strong enough to drag a mooring anchor across the seafloor, or energetic enough to push an autonomous vehicle off course faster than its propulsion system can compensate. The challenge for researchers planning deployments is that the current patterns are not fully predictable in advance. Models of the flow exist and they are improving, but the resolution of those models is not fine enough to reliably predict conditions at a specific location inside the trench on a specific day. There is a fundamental uncertainty in the environment that no amount of pre-expedition modelling can entirely eliminate. The equatorial crossing point adds another layer of complexity. The Coriolis effect, the deflection of moving objects caused by the Earth's rotation, operates differently at the equator than at higher latitudes. At the poles, the Coriolis effect is strongest. At the equator, it effectively disappears, and the transition zone near the equatorial line produces unusual behaviour in rotating fluid systems. Ocean currents that are well organised and predictable at higher latitudes can become less stable as they approach the equator. The deep circulation flowing through the Romanche is crossing this transition zone, and the consequences for current behaviour are not trivial. Some researchers have described the flow patterns in the equatorial Atlantic fracture zones as genuinely anomalous compared to what would be expected based on models built from higher latitude observations. The physics are not different exactly, but the combination of factors at the equatorial crossing point produces behaviour that is difficult to anticipate from first principles alone. There is also the question of what the seafloor itself looks like inside the trench, and what that means for anything trying to rest on it or move across it. The Romanche fracture zone is geologically active, sitting along a transform fault where two sections of the mid-Atlantic ridge are offset. The seafloor in this region is not the smooth, flat abyssal plain that characterises some parts of the deep ocean. It is rough, irregular, and in places dramatically so. Walls rise steeply on either side of the main trench axis. The floor itself is cut by smaller ridges and depressions. There are sills, which are raised sections of the seafloor that act as barriers to water flow, forcing the Antarctic bottom water to pool behind them before overflowing and cascading down the other side. These overflow events, when dense water spills over a sill and flows rapidly down the far side, are another source of energetic, turbulent flow inside the trench. They are not constant, but they are not rare either, and they are not always predictable from the outside. For an autonomous underwater vehicle trying to navigate this terrain, the challenges are considerable. The irregular topography means that pre-programmed navigation routes based on bathymetric maps may not accurately reflect the actual conditions the vehicle encounters. Maps of the Romanche floor, while improving, still contain gaps and uncertainties, particularly in the deepest and most remote sections of the trench. A vehicle navigating in a poorly mapped environment, in the presence of strong and variable currents, with limited ability to communicate with the surface, is operating with a significant margin of uncertainty at every moment. The vehicle's acoustic positioning systems, which allow it to determine its location relative to transponders deployed on the seafloor, can be disrupted by the same turbulent conditions that make the currents unpredictable. Sound travels through water, but it does not travel through water uniformly when that water is in turbulent motion, or when the temperature and density structure of the water column is highly variable. Acoustic signals can be bent, scattered, or obscured in ways that introduce errors into navigation and positioning. Mooring systems, which are anchored to the seafloor and carry instruments on a line that rises through the water column, face their own set of problems in this environment. A mooring is designed to stay in one place, recording data over a period of months or years, and then to be recovered by releasing the anchor weight and floating to the surface. The design assumes that the mooring line will remain roughly vertical, with the instruments sitting at their intended depths. In strong currents, this assumption fails. A mooring in a powerful current will be deflected, with the line pulled away from vertical and the instruments dragged to depths different from those intended. In an extreme case, the current can be strong enough to pull the entire mooring along the seafloor, dragging the anchor and depositing the instrument package somewhere other than where it was deployed. Recovery then becomes a matter of searching for something that may be kilometers from its last known position in deep water with limited acoustic contact. The combination of these factors, the extreme pressure, the near-freezing temperatures, the unusual current behavior driven by Antarctic bottom water flow and equatorial dynamics, the rough and incompletely mapped topography, and the energetic turbulence generated by flow over and around the fracture zone's internal structure, creates a physical environment that is not simply hostile in the way that all deep ocean environments are hostile. It is hostile in specific, compound, and in some respects genuinely unusual ways that require researchers to think carefully about which parts of the trench they can realistically study with existing technology and which parts remain for the moment effectively beyond reach. It is worth being clear about what this means and what it does not mean. Scientists do not avoid the Romanche because it is mysterious in some vague, unanswerable sense. They approach certain zones of it with particular caution, because the specific physical conditions in those zones have been shown, through experience and through modelling, to create elevated risks of equipment loss and failed deployments. This is not superstition. It is not institutional timidity. It is a rational response to a body of hard experience accumulated over decades of attempting to work in one of the most demanding environments on the planet. The caution is earned. And it is specific, focused on particular sections of the trench where the current behaviour is most energetic, the topography most difficult, and the conditions least predictable, rather than a blanket reluctance to engage with the trench at all. What makes this situation particularly interesting, and in some ways particularly frustrating for the scientists involved, is that the zones where the conditions are most challenging are often precisely the zones where the most scientifically important processes are occurring. the areas where Antarctic bottom water accelerates over sills and cascades into deeper basins, the areas where the fracture zone narrows and the flow becomes most energetic, the areas where turbulent mixing is most intense. These are the areas that matter most for understanding how the trench functions as a gateway in the deep Atlantic circulation. They are the places where the data would be most valuable, and they are also the places where deploying instruments is most difficult, most expensive, and most likely to result in loss. This tension between scientific importance and practical accessibility sits at the heart of why the Romanche remains so imperfectly understood despite being known to matter so much. The conditions described here are not static either. The flow of Antarctic bottom water through the Romanche varies over time, driven by changes in the formation rates of dense water near Antarctica and by broader shifts in the Atlantic circulation system. Some research suggests that the flow has changed measurably over recent decades, with implications for the temperature and oxygen content of the deep water downstream of the trench. Studying these changes requires long-term records, which in turn requires instruments that can survive in the trench environment for extended periods. The same conditions that make the trench difficult to study in the short term make long-term monitoring even more challenging. A mooring that needs to survive for a year or two in the energetic flow zones of the Romanche is asking a great deal of the engineering and a great deal of the luck that even the most carefully planned deep ocean deployments depend on to some degree. And it is precisely this challenge, the attempt to place instruments in a place that seems almost designed to reject them, and the consequences that have followed when those attempts have gone wrong, that forms the next part of the story. Because the physical conditions of the Romanche are not just an abstract engineering problem. They have produced a real, documented history of equipment lost, missions curtailed, and data never recovered. And that history has shaped, in quiet but measurable ways, how the scientific community thinks about what it is willing to risk in pursuit of what the trench might finally reveal. To understand what that history looks like in practice, it helps to spend some time with the water itself, not just the fact of its movement, but the character of it. Because the current behaviour inside the Romanche Trench is not simply a matter of water flowing quickly from one place to another. It is something more layered, more variable, and more difficult to anticipate than that description suggests. And the more closely scientists have looked at it, the more they have come to appreciate that the trench does not merely channel water through the equatorial Atlantic. It transforms it. It reshapes it in ways that ripple outward into the broader ocean for thousands of kilometres in every direction. The story begins, as so much of the deep Atlantic does, in the far south. Near Antarctica, during the coldest months of the southern winter, seawater at the surface is chilled to temperatures close to its freezing point. As it cools, it becomes denser. As sea ice forms, the salt that is excluded from the ice crystals concentrates in the surrounding water, making it denser still. This cold, salty, extraordinarily dense water sinks. It sinks not gently, not gradually, but with a kind of slow, inexorable weight that carries it all the way to the bottom of the ocean. Once it reaches the seafloor, it spreads northward, moving along the deep basins of the Atlantic in a mass of water that oceanographers call Antarctic bottom water. It is some of the densest, coldest water in the world's oceans, and it is one of the principal engines of the global circulation system that distributes heat, oxygen, and nutrients across the planet. The problem, from the perspective of Antarctic bottom water, making its way northward through the deep Atlantic, is that the ocean floor is not flat. The mid-Atlantic ridge runs roughly down the centre of the Atlantic basin like a long spine, and the deep basins on either side of it are largely separated from each other by this elevated terrain. Water, at the very deepest levels, cannot simply flow from one side to the other. It needs a gap. It needs a place where the ridge descends low enough, or where a fracture has cut deeply enough through it to allow passage. The Romanche Trench and the closely associated chain fracture zone nearby provides the most significant such passage along the equatorial segment of the ridge. It is, in effect, the primary doorway through which Antarctic bottom water crosses from the western Atlantic basin into the eastern one at depth. Without the Romanche, the deep eastern Atlantic would be a much more isolated environment, cut off from the ventilating influence of this cold, oxygen-rich southern water. The trench is not incidental to the deep Atlantic circulation, it is structural to it. What makes this relevant to the difficulty of working in the trench is what happens to Antarctic bottom water as it passes through that doorway. Dense water flowing through a constricted passage behaves according to principles that are well understood in theory, but genuinely dramatic in practice. As the water enters the narrowing geometry of the fracture zone, it accelerates. The same volume of water moving through a smaller cross-section must move faster, in the same way that a river quickens as it passes through a narrow gorge. Measurements taken in and around the Romanche have recorded current speeds that are remarkable by deep ocean standards, where the usual expectation is of water moving with a kind of glacial patience, shifting by centimetres per second rather than anything more vigorous. In the most energetic parts of the Romanche, the flow can be considerably faster than that, fast enough to matter greatly for anything placed in the water column. But speed alone does not fully capture what is happening. The flow through the Romanche is not a smooth, laminar current moving cleanly from one basin to the other. It is turbulent. It generates internal waves. It produces eddies and mixing events that are among the most intense recorded anywhere in the deep ocean. When dense Antarctic bottom water flows over the sills and ridges within the fracture zone and then descends into the deeper basins on the far side, it does not simply slide down the slope quietly. It plunges, it cascades, and as it does, it entrains surrounding water, mixing with it, drawing in warmer and lighter water from above and blending it into the descending plume. The result is a zone of turbulent mixing that is extraordinarily energetic by the standards of the deep sea, where mixing is usually so slow and so diffuse that it takes years or decades to produce measurable changes in water properties. This mixing matters enormously for the science. It is one of the primary mechanisms by which the deep ocean is ventilated, by which oxygen is carried downward and heat is redistributed. Understanding how much mixing occurs, where it occurs, and how it varies over time is central to building accurate models of the deep ocean's role in the climate system. But the same turbulence that makes the trench scientifically fascinating makes it practically treacherous for instruments. Internal waves, which are waves that propagate not at the surface of the ocean, but within its interior, along the boundaries between water layers of different density, can be generated in enormous numbers by the flow over the rough topography of the fracture zone. These waves can be large, they can carry significant energy, and they propagate away from their source in directions and at speeds that are not always easy to predict. An instrument moored in the water column of the Romanche is not sitting in still water. It is sitting in water that is being pushed and pulled by current fluctuations, swept by internal waves, and periodically subjected to the kind of energetic turbulence that can impose significant forces on anything anchored in place. A mooring line that is designed to remain roughly vertical may instead be swept into a pronounced lean, with the instruments on it displaced from their intended positions. The anchor that is meant to hold the mooring in place may be dragged across the seafloor if the current is strong enough and sustained enough to overcome the holding force of the anchor weight. And when the mooring is eventually commanded to release and float to the surface for recovery, it may surface kilometres from where it was deployed, if it surfaces at all. The unpredictability of the flow patterns compounds this problem in ways that are difficult to fully account for in advance. Oceanographers planning a deployment in a well-studied location can draw on years of historical current data to understand what conditions their equipment is likely to face. They can model the forces on their instruments and design their moorings accordingly. In the Romanche, the historical record of in situ current measurements is thin. The trench has not been visited often enough for long enough with enough instruments to build the kind of detailed picture of current variability that would allow confident engineering decisions. Each deployment is, to some degree, an experiment in itself, not just an attempt to collect data on the trench, but an attempt to learn whether the instruments can survive long enough to collect any data at all. There is also the question of what the flow does to the acoustic environment of the trench, and this matters more than it might initially seem. Modern deep ocean research depends heavily on acoustic technology. Acoustic releases are the mechanisms by which moored instruments are commanded to detach from their anchors and float to the surface. They work by sending a coded sound signal through the water, which the instrument hears and responds to by triggering a release mechanism. If the acoustic environment is too noisy, too variable, or too distorted by turbulence and internal waves, the signal may not reach the instrument reliably. A mooring that cannot hear its release command cannot be recovered. It sits on the seafloor indefinitely, its data inaccessible, its hardware lost. Acoustic Doppler current profilers, which are instruments that measure current speed and direction by sending sound pulses through the water and listening to how they are reflected back by particles in the flow, also depend on a reasonably well-behaved acoustic environment. In conditions of intense turbulence and rapid mixing, the structure of the water column can scatter and distort acoustic signals in ways that introduce errors into the measurements. A current profiler that is working hard to make sense of a highly disturbed acoustic environment may return data that is noisier, less precise, and more difficult to interpret than data collected in calmer conditions. The very conditions that make the trench interesting to study are the conditions that make studying it most technically difficult. Autonomous underwater vehicles, which have become increasingly important tools in deep ocean research over the past 2 decades, face their own particular challenges in the Romanche. These vehicles navigate by a combination of acoustic positioning, inertial navigation, and pre-programmed mission parameters. They are designed to operate in deep water without continuous communication with the surface, making their own decisions about how to follow their planned track. In the energetic flow of the Romanche, a vehicle's ability to follow a planned track is directly limited by how powerful its propulsion system is relative to the current it is trying to navigate through. A vehicle that can move at 1.5 meters per second through still water may find itself making very little headway against a current of comparable speed, burning through its battery reserves while covering far less ground than planned. If the current is strong enough, the vehicle may be unable to return to its launch point and may surface far from the ship, waiting to recover it. In the worst case, it may be swept into a part of the trench from which it cannot escape, its battery depleted, its mission incomplete. What all of this amounts to is a situation in which the Romanche Trench functions, in a very practical sense, as a place where the normal assumptions of deep ocean instrument deployment are less reliable than usual, not completely unreliable, not impossible to work in, but less reliable in ways that experienced researchers have learned to take seriously. The trench does not simply present the generic challenges of deep water work, the pressure, the darkness, the distance from the surface, the cost and complexity of ship time. It presents specific, additional challenges rooted in the particular behaviour of the water moving through it. And those challenges are concentrated most heavily in precisely the zones where the Antarctic bottom water flow is most energetic, most turbulent, and most scientifically consequential. One way to think about this is to consider what it would mean to try to measure a river at its most turbulent point. A calm stretch of river is relatively straightforward to instrument. You lower a sensor, it sits in the water, it records what passes by, you pull it back up. A stretch of river just below a waterfall where the water is churning and unpredictable and full of energy, moving in multiple directions at once, is a different proposition entirely. The sensor may be tumbled. The mounting may be stressed beyond its design limits. The data may be difficult to interpret because the flow is so complex. You can still try to measure it, and the measurement is arguably more important because so much is happening there. But you do so knowing that the instrument is working at the edge of what it was designed to handle. The Romanche, at its most active, presents something analogous to that situation, but at the bottom of the ocean, under 4,000 metres of water, with no possibility of quickly retrieving or adjusting the equipment if something begins to go wrong. It is also worth noting that the mixing behaviour of the trench is not uniform across its length or consistent through time. The fracture zone is not a simple channel. It contains internal sills, ridges and basins that create a complex three-dimensional flow structure. In some locations, the Antarctic bottom water cascades over a sill and mixes intensely as it descends. In others, it moves more quietly through a deeper passage. The turbulence is patchy, concentrated in specific areas that are not always easy to identify without detailed prior surveys. An instrument deployed slightly to one side of an intense mixing zone may experience relatively benign conditions, while an instrument a few hundred meters away may be in the middle of something far more energetic. Without a sufficiently detailed map of where the most active zones are, instrument placement is partly a matter of inference and partly a matter of chance. Some accounts from researchers who have worked in the region describe a quality of unpredictability that goes beyond what the general description of the trench might suggest. The flow can be relatively quiet for extended periods, and then shift into a more energetic state in ways that are not fully explained by the tidal forcing or the large-scale circulation patterns that drive most of the variability. There may be internal dynamics within the trench, interactions between the flow and the topography, or feedbacks within the mixing process itself that produce variability on timescales that are difficult to predict from external forcing alone. One explanation that has been discussed in the literature is that the turbulent mixing in the trench may be partly self-organising, with bursts of intense mixing generating internal waves that propagate through the fracture zone and interact with the flow in ways that trigger further mixing events. If this is the case, the trench has a kind of internal weather, a pattern of variability that is generated from within rather than simply imposed from outside. And internal weather by its nature is harder to forecast than weather driven by known external forcing. All of this, the accelerating currents, the cascading dense water, the internal waves, the turbulent mixing, the patchy and variable energy distribution, the acoustic complexity, the limits it places on every kind of instrument that scientists have tried to use there, forms the physical basis for the institutional caution that has accumulated around certain parts of the Romanche over decades of attempted study. It is a caution grounded not in speculation, but in experience, in ships that have returned with empty mooring lines, in acoustic releases that never responded, in vehicles that surfaced in the wrong place or not at all, in data records that ended abruptly, mid-deployment, for reasons that could only be guessed at from the surface. Each of those losses is a story in itself, a specific attempt to understand a specific part of the trench, thwarted by the very conditions that made the attempt worthwhile in the first place. And it is those stories, the documented record of what has actually been lost and what that loss has cost, that begin to explain why the reluctance to send expensive equipment into the most challenging zones of the Romanche is not simply caution in the abstract, but caution with a very concrete and specific history behind it. That concrete and specific history is worth sitting with for a moment, because it is not the kind of history that tends to make headlines. When a space mission loses a probe, the event is public, often dramatic, sometimes mourned in a way that feels almost personal. When an oceanographic institution loses a mooring in the Romanche Trench, the loss is recorded in a technical report, discussed at a conference, noted in a grant application, as a reason why the next deployment will require a different approach, and then quietly absorbed into the institutional memory of the people who were there. It does not disappear from the record, but it does not travel far beyond the community that understands what it means, and yet the accumulation of those losses over decades, across multiple institutions and multiple countries, has shaped the way the Romanche is approached in ways that are genuinely significant. The instruments that scientists deploy in deep ocean environments are not cheap in any sense of the word. A single deep sea mooring, the kind of system that anchors a line of sensors to the seafloor and holds them in place while they record data over months or years, can cost anywhere from tens of thousands to several $100,000, depending on its complexity, the sensors it carries, and the depth at which it must operate. A full lander, a self-contained platform that descends to the seafloor under its own weight, sits there collecting data and then releases its ballast and floats back to the surface, represents a similar order of investment. An autonomous underwater vehicle capable of operating at the depths found in the Romanche represents a substantially larger one. These are not figures plucked from imagination. They reflect the genuine cost of designing, building, testing, and deploying instruments that must withstand pressures equivalent to hundreds of atmospheres, function reliably in near-freezing water, and operate without any possibility of maintenance or adjustment for extended periods of time. When one of these instruments is lost, the financial impact is real and immediate. A research institution that loses a mooring in the Romanche does not simply note the loss and order a replacement. It faces a gap in its data record, a reduction in its available equipment, and a conversation with its funding body about what happened and what it plans to do differently. If the lost instrument was part of a larger observational program, its absence may compromise the integrity of data collected by other instruments in the same network. If it carried sensors that were unique or difficult to replace, the loss may delay research programs that depended on the data it was supposed to provide. And if the loss occurred during a deployment that was already expensive in terms of ship time and personnel, the total cost of the failed mission extends well beyond the value of the instrument itself. Ship time in the equatorial Atlantic is not inexpensive. Research vessels capable of operating in deep water, deploying and recovering heavy equipment, and maintaining the scientific staff needed to run a serious oceanographic expedition cost thousands of dollars per day to operate. An expedition to the Romanche might involve 2 or 3 weeks of ship time, which represents a substantial fraction of a research program's annual budget. If that expedition returns having lost one or more instruments, the institution must weigh the cost of a follow-up deployment against the competing demands of other research priorities, other instrument programs, other scientists waiting for ship time of their own. The economics of oceanographic research are not generous, and losses in difficult environments have a way of compounding over time in ways that are hard to recover from quickly. There are documented cases of equipment losses in the Romanche and the broader equatorial Atlantic fracture zone system, though the details tend to live in technical literature and expedition reports rather than in more widely read accounts. Researchers who have published on the deep circulation through the Romanche have noted, sometimes in the body of their papers and sometimes in the quieter language of acknowledgements and footnotes, that certain deployments did not go as planned. Moorings that were designed to be recovered were not. Acoustic releases that were supposed to respond to commands from the surface did not respond. Instruments that were tracked to the seafloor were not recovered when the ship returned. In some cases, the loss was attributed to equipment failure under the specific conditions of the trench. In others, the cause was simply listed as unknown, which in the context of deep ocean work is a category that covers a great deal of ground and resolves very little. What scientists have said publicly about these losses tends to be measured and professional, as one would expect from researchers who understand that equipment failure is a known risk in their field and who have no interest in dramatizing the difficulties of their work. But the measured language does not entirely conceal the frustration that accompanies losing months of preparation and significant resources to conditions that could not be fully anticipated or controlled. One way to read the published literature on the Romanche is as a record of careful, persistent attempts to understand a place that has repeatedly resisted the standard tools of the discipline. Each paper that reports partial data, interrupted time series, or deployment strategies modified in response to previous failures is, in a quiet way, a document of that resistance. The effect of repeated losses on institutional behaviour is not dramatic, but it is real. It is worth thinking of it less as a formal decision and more as a kind of accumulated wisdom that spreads through a community of researchers over time. A scientist who has lost equipment in the Romanche talks to colleagues about what happened. Those colleagues, when they are planning their own deployments, factor that experience into their thinking. Funding bodies that have reviewed proposals involving the Romanche develop a sense of the risk profile of those proposals. Program managers who allocate ship time and equipment budgets become aware that certain zones of the trench have a history of difficult recoveries. None of this produces a formal prohibition or an official designation of certain areas as off-limits. The process is subtler than that. It produces a kind of quiet institutional memory, a shared understanding that certain parts of the Romanche carry risks that go beyond the standard risks of deep ocean work, and that those risks have a track record of materializing in costly ways. The result is a pattern that can be observed in the distribution of observational efforts across the trench. The zones that are most scientifically interesting, the areas where the Antarctic bottom water flow is most energetic, where the mixing is most intense, where the turbulence is most pronounced, are also the zones where the history of instrument loss is most concentrated. And because those zones are where the loss history is most concentrated, they are also the zones where subsequent deployments have been planned most cautiously, with the most conservative assumptions about what the equipment can be expected to survive, and with the most careful attention to the possibility of failure built into the mission design from the start. Some deployments have been deliberately positioned to avoid the most energetic zones, accepting a less scientifically optimal location in exchange for a higher probability of successful recovery. Others have used shorter deployment periods, reducing the time the instrument spends in the trench, and therefore reducing the accumulated exposure to the conditions that have caused previous losses. These are rational adaptations to a difficult environment, but they come at a cost. Data collected from a less optimal position is less useful than data from the optimal position. A time series that runs for 3 months is less informative than one that runs for a year. Every compromise made in the name of equipment survival is also a compromise made in the name of scientific completeness. There is also a subtler effect that is harder to quantify but probably real. The Romanche has developed a reputation within the relatively small community of researchers who work on deep Atlantic circulation as a place where things go wrong. That reputation is grounded in fact, but reputations have a way of acquiring a life of their own that extends slightly beyond the facts that created them. A researcher who is considering a proposal involving the Romanche will be aware of that reputation and will factor it into their assessment of the proposal's risk. A funding body reviewing such a proposal will be similarly aware. The reputation does not make the research impossible, but it raises the bar for what a proposal must demonstrate in terms of risk mitigation and contingency planning before it is likely to be funded. And a higher bar for funding means fewer proposals submitted, which means fewer expeditions mounted, which means fewer data points collected, which means the gaps in our understanding of the trench remain wider than they would otherwise be. It is a cycle that is not easy to break, because the best way to break it would be a series of successful deployments that rebuilt confidence in the trench as a workable environment. And mounting those deployments requires overcoming the very institutional reluctance that the previous losses created. It is also worth noting that the losses in the Romanche are not simply a matter of bad luck or inadequate technology. Some of the instruments lost there were state-of-the-art at the time of their deployment. Some of the moorings that failed to be recovered were designed by experienced teams who had successfully operated similar systems in other deep ocean environments. The Romanche did not defeat poorly designed equipment deployed carelessly. It defeated well-designed equipment deployed carefully by experienced researchers who understood the risks they were taking and took them anyway because the scientific questions were important enough to justify the attempt. That is a different kind of story, and it carries a different kind of weight. It suggests that the challenges of the trench are not simply a matter of needing better technology or more careful planning, though both of those things matter. It suggests that the Romanche presents a genuinely unusual set of conditions that push against the limits of what current deep ocean instrumentation can reliably handle in its most energetic zones. The autonomous underwater vehicles that have been sent into the trench have had their own complicated histories. These vehicles, which navigate independently along pre-programmed routes and surface at designated times and locations to transmit their data and be recovered, are designed to handle the general challenges of deep ocean operation. But the Romanche, as has been noted, does not present only the general challenges. The strong and variable currents that move through the fracture zone can push an autonomous vehicle off its planned route, in ways that accumulate over the course of a long dive. A vehicle that enters the trench on a carefully planned trajectory may find, hours later, that the currents have carried it significantly away from its intended position. If the vehicle's navigation system is not able to compensate fully for that displacement, its data may not correspond to the locations it was intended to sample. And if the displacement is large enough, the vehicle may surface far from where the ship is waiting, requiring an extended search and recovery operation that consumes time and fuel and adds stress to an already expensive mission. In the more serious cases, vehicles have not surfaced at all, or have surfaced in conditions that made recovery impossible. The equatorial Atlantic is not a benign environment at the surface either. Weather in that region can change quickly, and a vehicle that surfaces into rough conditions, or at a location that is difficult for the ship to reach safely, may be lost even after it has successfully completed its dive. The combination of deep water challenges and surface recovery challenges creates a situation in which the probability of a fully successful mission, one in which the vehicle dives, collects its data, and is recovered intact, is lower than in more benign environments. And lower probability of success, repeated across multiple expeditions, is what produces the pattern of losses that has accumulated in the institutional memory of the field. What is perhaps most striking about all of this, when you step back and consider the full picture, is that the losses and the caution they have generated exist in direct tension with the scientific importance of the zones that are most difficult to study. The areas of the Romanche where equipment is most likely to be lost are also the areas where the most important scientific processes are occurring. The intense mixing zones, the regions of strongest flow, the places where the Antarctic bottom water cascades over the internal sills and generates the turbulence that transforms its properties before it continues into the North Atlantic. These are precisely the places where measurements are most needed and most difficult to obtain. The trench is not withholding unimportant information in its most challenging zones. It is withholding some of the most consequential information available about how the deep ocean circulation works and how it might respond to a changing climate. And the instruments that could collect that information are the ones most likely to be lost in the attempt. That tension between the importance of the measurement and the difficulty of making it, between the value of the data and the cost of pursuing it, is what gives the story of equipment losses in the Romanche its particular character. It is not simply a story of things going wrong in a difficult place. It is a story of a scientific community doing its best to understand something that matters enormously in a place that makes understanding genuinely hard, and accumulating a quiet record of the price that has been paid for every partial success and every outright failure along the way. The instruments that have been lost in the Romanche are not simply gone. They are part of the evidence base for why the trench is the way it is, and why studying it requires more than standard approaches can reliably provide. And that evidence base, the accumulated record of what has been tried, and what has been lost and what has been learned from both, is also part of what makes the biology of the Romanche such an interesting and largely open question. Because if the physical conditions of the trench are challenging enough to defeat some of the most sophisticated instruments that oceanographers have designed, one naturally begins to wonder what those conditions mean for the organisms that actually live there, in the dark, under the pressure, inside the current, without the option of surfacing to safety when things become difficult. And that is where the story becomes something else, entirely. Because the Romanche Trench is not simply a passage for cold water, not simply a graveyard for expensive instruments, not simply a difficult place on a map. It is also a habitat. It is home, in the fullest sense of that word, to organisms that have never seen sunlight, that have never known any temperature other than the near-freezing cold that flows through from the south, that have built their entire existence around conditions that would be lethal to almost every other form of life on the planet. And what is remarkable, and perhaps a little humbling, is how little we actually know about them. The deep ocean in general remains one of the most biologically underexplored environments on Earth. That statement has been made so many times in so many science documentaries and popular articles that it can start to feel like a formality, a polite disclaimer before getting to the real information. But in the case of the Romanche Trench specifically, the statement carries particular weight. Most deep ocean environments that have received sustained scientific attention, the Mariana Trench, the Puerto Rico Trench, portions of the deep Pacific and Indian Ocean floors, have accumulated at least a working picture of their biological communities over decades of sampling. Researchers have catalogued species, described food webs, identified the dominant organisms, and developed at least a partial understanding of how life organises itself at extreme depth. The Romanche has not received that kind of sustained attention. The biological picture that exists for this trench is fragmentary in a way that goes beyond the usual incompleteness of deep-sea science. It is not that we have a rough outline and are missing the details. It is that in many zones of the trench, we do not yet have a reliable rough outline. What we do have comes from a small number of sampling events spread across a long span of time, with significant gaps between them. Early biological collections from the region were made with the limited tools of their era, trawl nets and dredges lowered on cables, which collected whatever happened to be in their path, but could not target specific depths or habitats with any precision. These early samples did confirm that life existed at depth in the Romanche region, which was itself a meaningful finding for its time, but they could not tell researchers much about how that life was structured, how abundant it was, or how it compared to communities in other deep environments. They were snapshots taken in the dark with a very wide lens, capturing fragments of something whose full shape remained invisible. Later expeditions, equipped with more sophisticated tools, have added pieces to the picture. Sediment cores taken from the trench floor have yielded microbial communities, the single-celled organisms that form the base of many deep-sea food webs, and that are often the most abundant form of life in extreme environments. These microbes are not dramatic in the way that larger deep-sea animals tend to be. They do not glow in the dark or have rows of transparent teeth, but they are ecologically foundational. They process organic matter, cycle nutrients, and support whatever larger life exists above them in the food web. Their presence in the Romanche sediments is not surprising, but the specific composition of the microbial communities there, which species are present, what metabolic strategies they use, how they compare to microbial communities in other deep trenches, remains poorly characterized. The samples that have been collected are few enough that drawing confident conclusions from them feels premature. What makes the biology of the Romanche particularly interesting, and particularly difficult to predict from first principles, is the unusual combination of environmental conditions that the trench presents. Most deep ocean trenches sit in relatively stable thermal environments. The water at depth is cold, but it tends to be cold in a consistent way that reflects the regional oceanographic setting. The Romanche sits at the equator, which means that the water above the trench, in the upper ocean layers, is warm. Tropical warm. The surface waters of the equatorial Atlantic are among the warmest in the world ocean. But the deep water flowing through the trench from the south is Antarctic bottom water, which is among the coldest water in the world ocean. The result is an environment where the temperature gradient from surface to depth is exceptionally steep, where warm tropical surface conditions and near-freezing abyssal conditions exist in the same vertical column of water, separated by a thermocline that is more pronounced than in most other locations where deep trenches occur. What this means for biology is not entirely clear, and that uncertainty is itself part of what makes the Romanche interesting. In some deep-sea environments, the steep gradient between warm surface waters and cold deep waters can create conditions that support relatively high biological productivity. because the mixing of water masses can bring nutrients to the surface where photosynthesis is possible, and organic material produced at the surface can sink to the deep and support communities below. Whether the specific dynamics of the Romanche enhance or suppress biological productivity in this way is something that has not been thoroughly studied. The unusual current behaviour in the trench, the turbulence and internal waves and strong mixing that have been described in the physical oceanography literature, could in principle affect the transport of organic material through the water column in ways that differ from more quiescent deep environments. Whether that means the biological communities of the Romanche are richer or poorer than those of comparable trenches is an open question. Some of the most intriguing, if limited, biological findings from the Romanche region have come from the collection of megafaunal organisms, the larger animals that inhabit the deep-sea floor and water column. Deep-sea trenches around the world have yielded remarkable creatures, some of them entirely new to science at the time of their discovery, some of them representing lineages that had not been observed alive before. Giant amphipods, unusual species of sea cucumbers, fish adapted to extreme pressure, polychaete worms of unexpected size and complexity. The deep trenches of the Pacific in particular have been the source of numerous species descriptions and biological surprises. The Romanche has yielded some organisms of interest as well, collected in the limited sampling events that have reached its depths, but the inventory is thin. The number of species formally described from Romanche samples is a fraction of what has been catalogued from better studied trenches, and the fraction is not simply a reflection of the trench being biologically impoverished. It is a reflection of how rarely anyone has been able to collect samples from it. One of the specific biological questions that researchers have found difficult to answer concerns the degree to which the organisms of the Romanche are connected to, or isolated from, the biological communities of other deep Atlantic environments. Deep ocean trenches can function as either corridors or barriers for marine life, depending on the species and the specific geography involved. Some organisms move freely between deep environments, dispersing along the ocean floor or through the water column in ways that keep populations connected across large distances. Others are highly localized, restricted to specific trenches or basins by the same physical barriers that make the trench a significant feature in the circulation of the deep ocean. Whether the Romanche functions primarily as a corridor, allowing organisms to move between the deep South Atlantic and the deep North Atlantic, along with the Antarctic bottom water that flows through it, or primarily as an isolated habitat with a distinct biological community, is something that has not been definitively established. The physical evidence suggests that the trench is a genuine passage for water masses, which might imply that it is also a passage for organisms. But the biological sampling needed to test that idea has not been done at the scale required to answer the question confidently. The microbial dimension of this question is particularly interesting, because microbes are, in many deep-sea environments, the most ecologically significant organisms present. They are the primary processors of organic carbon, the drivers of nutrient cycles, and in some environments the base of food webs that are entirely independent of photosynthesis, relying instead on chemosynthesis, the metabolic process by which certain microbes derive energy from chemical reactions rather than sunlight. Hydrothermal vents and cold seeps support entire ecosystems built on chemosynthesis, and while the Romanche Trench is not known to host active hydrothermal venting in the way that some other parts of the mid-Atlantic ridge do, the geological setting of the trench, along a transform fault zone in an area of tectonic activity, means that the possibility of fluid seepage and chemosynthetic communities cannot be ruled out without more thorough investigation. Some accounts suggest that the sediments and rock formations of the trench floor have not been surveyed with sufficient resolution to determine whether such features exist there. It is possible that chemosynthetic communities are present in the Romanche and have simply not been found because no one has looked in the right places with the right tools. That possibility, modest as it might sound, is actually quite significant. chemosynthetic ecosystems at deep sea vents and seeps have proven to be among the most biologically diverse and ecologically distinctive environments on the planet. They support organisms found nowhere else, adapted to conditions that would be lethal in other contexts, and they have expanded scientific understanding of the range of conditions under which life can persist and flourish. If the Romanche were to host such communities, even on a small scale, it would represent a significant biological finding. But the combination of the trench's physical challenges and its relative neglect in the scientific literature means that this question remains genuinely open in a way that similar questions have been resolved for better studied environments. There is also the matter of what the Antarctic bottom water itself brings to the biology of the trench. This water, which originates in the Southern Ocean around Antarctica, is not biologically empty when it enters the Romanche. It carries with it organic particles, dissolved organic matter, and microbial communities that have been transported from their origin point over the long journey northward along the ocean floor. What happens to these biological passengers when they pass through the turbulent mixing environment of the Romanche is not well understood. The intense physical mixing that transforms the water's temperature and salinity properties as it passes through the trench could also affect its biological content, either by disrupting microbial communities, by creating conditions that favour certain organisms over others, or by concentrating organic material in ways that support local biological activity. These are not fanciful speculations, they are reasonable hypotheses based on what is known about how physical oceanographic processes interact with biological communities in other environments. But they remain hypotheses because the measurements needed to test them have not been made in sufficient detail. What is clear, from the limited evidence that does exist, is that life in the Romanche is not absent. The trench is not a biological desert. Organisms are present at depth, microbes are present in the sediments, and the broader region supports a range of deep sea life that reflects the general patterns of the deep Atlantic. What is not clear is the full character of that life, its diversity, its structure, its ecological relationships, its degree of distinctiveness from other deep Atlantic communities, and its potential to harbour species or communities that have not yet been described. The gaps in the biological survey of the Romanche are not gaps that can be filled by inference from other environments. The unusual physical conditions of the trench, the equatorial location combined with Antarctic bottom water, the intense mixing and turbulence, the geological setting along a transform fault, mean that the Romanche is different enough from other deep environments that its biology may well be distinctive in ways that cannot be predicted from what is known elsewhere. And so, the organisms of the Romanche Trench live in a kind of double obscurity. They are hidden first by the depth and darkness that conceals all deep sea life from casual observation, and hidden again by the physical conditions that have made the trench so difficult to study that even the scientific community has only the most fragmentary knowledge of what lives there. They are in a sense doubly unknown. Unknown to the general public in the way that all deep sea life is unknown, and unknown to the scientific community in a more specific and more troubling way, because the tools and expeditions that would normally begin to resolve that unknowing have been defeated often enough, and the logistical barriers have been high enough that the biological inventory of the Romanche remains one of the most incomplete for any major deep ocean feature on the planet. That incompleteness is not merely a gap in a catalogue. It represents a genuine scientific uncertainty about the living world of a place that is, by any measure, one of the most physically distinctive deep ocean environments on Earth. And as the story of the Romanche continues to unfold, slowly and with considerable difficulty, that biological uncertainty sits alongside the physical and engineering challenges as one of the reasons the trench commands a particular kind of scientific attention, even when the practical barriers to studying it remain formidable, because what the trench may be hiding in its biology is as consequential, in its own way, as what it is hiding in its geology and its currents. And the geology, it turns out, has its own complicated story to tell about why the Romanche is the kind of place that gives careful scientists reason to pause before they commit their instruments, their budgets, and their plans to its depths. The geology of the Romanche Trench is not incidental to its character. It is, in a very real sense, the reason the trench exists at all, and it is also one of the most significant reasons that careful scientists approach certain zones of it with a particular kind of institutional caution that goes beyond the ordinary challenges of deep-sea research. To understand why, it helps to return to the basic structural fact of the Romanche, which is that it does not sit in geologically quiet territory. It sits along a transform fault, one of the most seismically active types of plate boundary on Earth, and that fact carries consequences that extend from the floor of the trench all the way to the surface decisions made in university offices and funding committees. A transform fault, in the simplest terms, is a boundary where two tectonic plates are not pulling apart or pushing together, but sliding past each other horizontally. The Mid-Atlantic Ridge, which runs roughly down the centre of the Atlantic Ocean, is primarily a divergent boundary, a place where the African and South American plates are slowly separating, a new seafloor is being created between them. But the ridge is not a single straight line. It is broken into segments, offset from one another by fracture zones, and the Romanche fracture zone is one of the largest and most significant of these offsets. Along the fracture zone, the movement is not divergent but lateral, with the two sides of the fracture sliding past each other as the broader spreading process continues. That lateral motion is what creates the transform fault, and transform faults are, by their nature, places where stress accumulates and is periodically released in the form of earthquakes. The seismic history of the Romanche region is not dramatic in the way that, say, the subduction zones of the Pacific are dramatic. It does not produce the catastrophic megathrust earthquakes that have reshaped coastlines and generated devastating tsunamis in other parts of the world, but it does produce a steady background of seismic activity, punctuated by events of meaningful magnitude that reflects the ongoing tectonic motion along the fracture zone. Earthquakes in the magnitude 5 and 6 range have been recorded in the region with some regularity, and larger events are not unknown. These are not trivial numbers when one is thinking about the long-term placement of scientific instruments on the ocean floor, or about the structural stability of the trench walls themselves. The walls of the Romanche Trench are, by the standards of deep ocean features, quite steep. The trench is not a broad, gently sloping depression, but a relatively narrow, sharply defined structure, and the walls that define it rise steeply from the trench floor to the surrounding seafloor level. Steep walls in a seismically active environment are walls that are susceptible to failure. Submarine landslides, which in the deep ocean are more accurately called mass-wasting events, are a recognised hazard in tectonically active deep-sea environments, and the combination of steep slopes, fractured rock, and periodic seismic shaking creates conditions that can trigger such events. When a mass-wasting event occurs on the wall of a deep trench, the consequences for anything resting on or near the trench floor can be severe. Sediment avalanches, turbidity currents, and the physical impact of displaced material can destroy instruments, bury mooring anchors, and alter the local topography in ways that make subsequent survey data difficult to interpret against earlier baselines. This is not a purely theoretical concern. Turbidity currents, which are essentially fast-moving underwater avalanches of sediment and water, are a known feature of tectonically active deep-sea environments, and they can travel at speeds and with forces that are difficult to appreciate from a surface perspective. A turbidity current moving down the steep wall of the Romanche and across its floor would carry enough energy to sweep away or bury scientific instruments that had been carefully placed and anchored to the sea floor. The anchoring systems used for deep-sea moorings are designed to resist the ordinary currents and forces of the deep ocean environment. But a turbidity current is not an ordinary force. It is in some respects more analogous to a flash flood than to a persistent current, and the instruments designed to withstand the latter may not survive the former. What makes this particularly relevant to the question of scientific caution around the Romanche is that the timing of such events is not predictable in any operationally useful way. Seismic events along the fracture zone do not announce themselves in advance. The relationship between a given earthquake and any subsequent mass wasting or turbidity current activity is not deterministic. A moderate earthquake might trigger a slope failure immediately, or it might contribute to the gradual weakening of a slope that eventually fails days or weeks later, or it might have no visible consequence at all. This uncertainty means that a research team cannot simply monitor seismic activity and choose to deploy instruments during a quiet period, because the quiet period offers no guarantee against a subsequent event, and because the instruments, once deployed, are typically left in place for months or even years before recovery is attempted. The practical implication is that any instrument placed in the Romanche is placed with the knowledge that the geological environment around it may change in unpredictable ways during the deployment period. That knowledge does not necessarily prevent deployments from being planned and executed, but it does factor into the risk calculations that scientists and funding bodies must make when deciding whether the scientific value of a particular measurement justifies the cost and likelihood of loss. And when those calculations are made against the backdrop of the equipment losses and retrieval failures that have already characterized work in the trench, the geological risk adds another layer of institutional hesitation that is not always explicitly stated but is nonetheless real. There is also the question of what seismic activity does to the water column above the trench. Earthquakes along the Romanche fracture zone can generate internal waves in the deep ocean, disturbances that propagate through the water column at depth rather than at the surface, and that can have significant effects on instruments and moorings. Internal waves generated by seismic events or by the sudden displacement of the seafloor can interact with the already complex current and turbulence environment of the trench in ways that are difficult to model and that can impose forces on instrument packages beyond what their design specifications anticipate. The combination of unusual hydrodynamic conditions that already characterizes the Romanche, the strong Antarctic bottom water flow, the internal tidal waves, the turbulent mixing with the additional perturbations that seismic activity can introduce, creates an environment where the forces acting on a deployed instrument are genuinely harder to predict than in most other deep ocean settings. For any future crewed mission to the Romanche, these geological considerations would carry even greater weight. The deep-sea submersibles that have been used in other trench environments, including the Mariana Trench, are engineered to withstand extraordinary pressure, but they are not designed to operate in environments where the seafloor might suddenly shift, where walls might shed material without warning, or where the water column might be disturbed by seismic energy in ways that affect vehicle control and stability. The logistical planning for a crewed descent into a seismically active trench would require a level of real-time seismic monitoring and operational flexibility that adds considerably to the complexity and cost of such a mission. It is not that a crewed descent into the Romanche is impossible in principle. It is that the geological environment of the trench demands a degree of caution and preparation that goes beyond what is required for descents into geologically quieter, deep ocean environments, and that additional demand has its own effect on the calculus of whether and when such missions get planned and funded. Remotely operated vehicles and autonomous underwater vehicles face a somewhat different version of the same problem. They do not carry human lives, which removes the most immediate and visceral dimension of the risk, but they represent significant financial investments, and their loss or damage in a seismically triggered event would set back research programs in ways that are both material and motivational. There is a quiet but real institutional psychology around the repeated loss of expensive equipment in a particular location. It is not that scientists become superstitious about a place exactly, but that the cumulative experience of failed deployments and lost instruments creates a kind of institutional memory that shapes how proposals are written, how reviewers evaluate risk sections, and how cautiously program managers approach new commitments to a site that has proven expensive and unreliable in the past. The geological instability of the Romanche also has implications for the long-term interpretation of the data that does get collected there. sediment cores extracted from the trench floor, which represent one of the primary tools for reconstructing the geological and paleoceanographic history of the site, must be interpreted with an awareness that the sedimentary record in a tectonically active steep-walled trench may be interrupted or disturbed by mass-wasting events. A core that appears to show a continuous record of sedimentation may in fact contain layers that have been transported from elsewhere on the trench wall, or may be missing intervals that were eroded or displaced by past turbidity currents. Disentangling the in-situ record from the transported and reworked material requires careful analysis, and, ideally, multiple cores from different locations within the trench to identify which features are consistent across the site and which are local artifacts of past disturbance events. That kind of comprehensive coring program has not been carried out in the Romanche, partly because of the logistical barriers and partly because the seismically active environment makes the interpretation of any individual core more complicated and more uncertain from the outset. There is something almost paradoxical about this situation when you step back and consider it. The geological activity that makes the Romanche difficult and risky to study is also the geological activity that makes it scientifically interesting in the first place. The transform fault that generates seismic events and creates the risk of slope failure is also the structure that formed the trench itself and that continues to shape its unusual physical character. The steep walls that might shed material onto deployed instruments are also the walls that expose deep crustal rock in ways that offer rare windows into the composition and structure of the oceanic lithosphere. The same tectonic forces that create operational hazards are the forces that have made the Romanche a place of genuine geological significance, a place where the processes that build and reshape the ocean floor can be observed in unusually direct and accessible ways, if one can manage to get instruments there and keep them working long enough to collect useful data. This paradox is not unique to the Romanche. Many of the most scientifically interesting places on Earth are interesting precisely because they are geologically active, and geological activity tends to create both the conditions that attract scientific attention and the conditions that make scientific work difficult. Active volcanoes, fault zones, subduction trenches, and hydrothermal vent fields all share this quality of being simultaneously compelling and hazardous. But the Romanche sits at a particular intersection of geological interest and operational difficulty that has, so far, prevented the kind of sustained, systematic investigation that would begin to resolve the many questions the trench raises about deep ocean geology, circulation, and biology. For now, the geological story of the Romanche remains, like its biological and physical oceanographic stories, a story told in fragments. There are data points, isolated measurements, single cores, limited seismic surveys, and the interpretations that careful scientists have built from those incomplete foundations. But the full picture, the kind of comprehensive understanding that comes from repeated visits, multiple instrument deployments, sustained monitoring, and the patient accumulation of evidence across different methods and timescales, that picture has not yet been assembled. And one of the reasons it has not is that the geology of the Romanche, the very forces that made it what it is, continues to make the work of understanding it considerably more difficult than the work of understanding most other places at comparable depth. It is worth pausing for a moment on what this means in the broader context of how science actually gets done. The image of scientific exploration as a steady, rational march toward understanding, limited only by the pace of technological development, is not quite accurate when applied to places like the Romanche. The decisions about where to send ships and instruments, how much risk to accept, how to weigh scientific value against financial cost and operational hazard, these are not purely technical decisions. They are human decisions, shaped by institutional cultures, funding pressures, professional incentives, and the accumulated experience of previous attempts. The geological instability of the Romanche feeds into all of those dimensions of decision-making, not as a single decisive factor, but as one persistent element in a complex calculation that has, repeatedly, produced the same outcome. The trench remains understudied. the questions it raises remain open, and the next expedition, when it comes, will face a geological environment that has not become any simpler or more forgiving in the intervening years, which brings the story, inevitably, to the question of who has actually tried, who has actually committed ships and funding and scientific plans to the challenge of the Romanche, and what the broader logistical and geopolitical landscape looks like for a place that sits in the middle of the equatorial Atlantic, far from the major oceanographic institutions that have the resources to study it. Because the geology of the trench is only one part of the barrier. The practical reality of getting a research vessel to that location, keeping it on station long enough to do meaningful work, and navigating the complex international and institutional frameworks that govern scientific work in the deep ocean, those realities form their own complicated layer of the story. And they help explain, in ways that have nothing to do with pressure or earthquakes or turbidity currents, why the Romanche has remained as unknown as it has for as long as it has. So let us follow that thread where it leads, because the practical landscape surrounding the Romanche is, in its own way, just as formidable as anything the geology or the physics of the trench itself can throw at a research team. And it begins with a question that sounds almost administrative until you realise how much weight it carries. Who exactly is responsible for this place? The Romanche Trench sits almost entirely within what is known as the high seas, the international waters of the equatorial Atlantic that fall outside the exclusive economic zones of any individual nation. In principle, this means it belongs to everyone. In practice, it means it belongs to no one in particular, and that distinction matters more than it might initially seem. When a body of water falls within a nation's exclusive economic zone, that country has both the authority and, in many cases, the incentive to study it. The deep ocean beneath their waters is, among other things, a potential resource, a source of scientific prestige, and a zone of strategic interest. Governments fund surveys. National oceanographic institutions build programs around nearby features. There is a constituency, however small, that has a reason to care. The Romanche, sitting in international waters roughly equidistant from the coasts of South America and West Africa, does not benefit from that kind of proximity-driven attention. No single nation looks at the Romanche and sees it as theirs to understand. It is a shared inheritance that, like many shared inheritances, tends to remain unclaimed. The countries that sit closest to the trench geographically are the nations of West Africa, and, on the other side of the Atlantic, the northern coast of Brazil. None of these nations has, historically, maintained the kind of large-scale, deep-sea research infrastructure that would make mounting a major Romanche expedition a straightforward institutional decision. The major oceanographic powers, the institutions in the United States, the United Kingdom, France, Germany, and a handful of other countries that have historically driven deep ocean research, are all considerably farther away. And distance in oceanography is not merely a matter of geography. It is a matter of time at sea, fuel costs, vessel scheduling, and the complex logistics of keeping a research ship on station in the open equatorial Atlantic for weeks at a stretch. To understand what this means practically, it helps to think about what a serious deep-sea research expedition actually involves. A modern oceanographic research vessel, capable of deploying the kind of equipment needed to study a trench like the Romanche, is not a small or inexpensive thing to operate. Day rates for major research vessels, including crew, fuel, maintenance and support, can run into figures that make even experienced scientists wince when they write grant applications. A single research cruise lasting 3 to 4 weeks, which would represent a fairly minimal investment in terms of what the Romanche actually requires, might consume a budget that a mid-sized oceanographic research program would normally spread across an entire year of work. And that is before accounting for the cost of the specialised instruments that would need to be deployed, many of which, as earlier parts of this story have established, carry a genuine risk of not coming back. For institutions based in North America or Europe, the Romanche is not a convenient detour. It is not a site that can be visited on the way to somewhere else, squeezed into a cruise schedule that is primarily focused on a different region. It sits in a part of the Atlantic that requires a dedicated expedition, planned specifically for that location, with all the funding and logistical commitment that implies. The equatorial Atlantic is not a region where major oceanographic institutions maintain routine research programs, partly because the most intensively studied features of the Atlantic, the North Atlantic circulation system, the deep water formation zones in the North Atlantic and the Southern Ocean, the well-documented current systems of the subtropical gyres, lie elsewhere. The equatorial region is, in a sense, the middle of the story, the part that connects the northern and southern chapters, but does not itself tend to attract the sustained institutional attention that the endpoints receive. There is also the question of how scientific funding actually works, which is a topic that does not often appear in documentaries about ocean exploration, but which shapes the landscape of what gets studied and what does not more profoundly than almost any other single factor. In most of the major oceanographic nations, research funding is allocated through competitive grant processes in which scientists propose projects, panels of reviewers evaluate those proposals, and money flows toward the work that is judged most likely to produce significant results within a defined time frame. This system has genuine strengths. It encourages rigour, it allocates limited resources toward high-priority questions, and it creates accountability for how public or institutional money is spent. But it also has a particular weakness when it comes to places like the Romanche. The problem is that the Romanche is, by definition, a place about which very little is known. And in a competitive funding environment, it is considerably easier to write a compelling grant proposal about a place where enough is already understood to frame a specific, answerable scientific question than it is to write a compelling proposal about a place where the honest answer to almost every question is simply that no one knows. Proposals to study the Romanche must essentially argue for the value of exploration itself, for the importance of going to a place that is known to be scientifically significant without being able to specify precisely what will be found or what questions will be resolved. That kind of argument is harder to make persuasively in a system designed to evaluate the likely return on a specific scientific investment. It is not impossible, but it faces structural headwinds that more mature research programs, built around well-understood systems where the next question follows logically from the previous answer, do not encounter in the same way. This creates what might be described as a knowledge gap that feeds on itself. Because so little is known about the Romanche, it is difficult to secure funding to study it. Because funding is difficult to secure, expeditions are rare. Because expeditions are rare, knowledge accumulates slowly. Because knowledge accumulates slowly, the gap between what is known and what would need to be known to write a compelling specific scientific proposal remains wide. And so the cycle continues, not because of any deliberate neglect, and not because scientists are unaware of the trench's significance, but because the institutional structures through which science is funded and organised tend to reward depth of knowledge in familiar systems rather than breadth of exploration in unfamiliar ones. It is worth noting that this dynamic is not unique to the Romanche, and it is not unique to oceanography. It appears wherever the frontier of knowledge runs up against the practical requirements of institutional science. The history of exploration is full of places that were known to exist, suspected to be important, and left unstudied for decades or generations simply because the combination of logistical difficulty and institutional inertia was sufficient to keep expeditions from being mounted. The Romanche is a contemporary example of a very old problem, which is that the most interesting places are often the hardest to get to, and the hardest to get to are often the hardest to fund. And the hardest to fund are often the least studied, regardless of their scientific importance. The countries that have made attempts at studying the Romanche or its immediate environs represent a relatively short list. French oceanographic institutions have historically been among the most active in the equatorial Atlantic, partly because of France's geographic position and its long tradition of deep-sea research, and partly because of the institutional legacy of figures like Jacques Picard and the broader French investment in ocean science that developed through the latter half of the 20th century. German research vessels have also visited the region on various occasions, contributing measurements and samples that have added to the limited body of data on the trench. American institutions, including those associated with the Woods Hole Oceanographic Institution and the Scripps Institution of Oceanography, have conducted work in the broader equatorial Atlantic that has touched on the Romanche in various ways. Though sustained, focused campaigns specifically targeting the trench have been less common than one might hope given its significance. What these expeditions share, almost without exception, is a quality of incompleteness. Ships have visited, measurements have been taken, instruments have been deployed with varying degrees of success, and data has been collected and published. But the visits have been separated by long intervals, sometimes measured in decades rather than years, and the cumulative picture they produce is one of isolated data points rather than the kind of continuous, multi-method monitoring that would allow scientists to characterize the trench's behavior across different timescales and seasons. One expedition might document the water chemistry of the Antarctic bottom water, passing through the trench at a particular moment. Another, years later, might collect sediment cores from a different part of the trench floor. A third might deploy acoustic instruments to measure current speeds for a limited period. Each of these contributions is genuinely valuable, but they do not add up to a comprehensive understanding of the system in the way that a coordinated, sustained research program would. There is also a dimension of international coordination that complicates the picture further. Deep-sea research in international waters operates within a framework of international agreements and norms that are, in some respects, well developed, and in others, still evolving. The question of who has the right to collect samples from the deep seabed in international waters, how those samples can be used and who benefits from any knowledge or resources derived from them is a matter of ongoing international negotiation. The United Nations Convention on the Law of the Sea, which governs many aspects of maritime activity, addresses some of these questions, but the deep seabed in international waters falls under a particular legal regime administered by the International Seabed Authority, and the practical implications of this regime for scientific research are not always straightforward. For institutions planning expeditions to the Romanche, navigating this legal and regulatory landscape is an additional layer of complexity on top of the already substantial scientific and logistical challenges. None of this is to suggest that the international framework is the primary barrier to Romanche research. It is not. The cost, the distance, the equipment challenges, and the institutional dynamics of scientific funding are all more immediately limiting factors. But the regulatory dimension adds a layer of administrative complexity that consumes time and resources during the planning phase of any expedition, and that can, in marginal cases, tip the balance toward choosing a different study site, where the paperwork is simpler and the precedents are clearer. What emerges from all of this, when you step back and look at the full picture, is a portrait of a place that has been caught in a kind of institutional no man's land for most of the history of modern oceanography. Too deep and too remote to be studied casually, too isolated from the major oceanographic centres to attract sustained institutional attention, too poorly understood to generate the kind of specific, answerable scientific questions that funding panels reward, too seismically active and hydraulically turbulent to be studied cheaply or reliably, and sitting in international waters that belong to everyone and therefore in practice to no one. Each of these factors, taken individually, might be overcome. Taken together, they have been sufficient to keep the Romanche in a state of relative scientific obscurity for longer than most researchers who know the trench would consider acceptable given its importance. There is a certain irony in the fact that the Romanche, which sits almost exactly on the equator, the great geographic midline of the planet, should be so marginal in the geography of scientific attention. The equator is not a peripheral concept. It is, in many ways, the centre, the point from which latitude is measured, the zone where solar energy input is highest, and where the atmospheric and oceanic circulation systems that drive weather and climate across the entire planet are energized. And the Romanche, sitting at the equatorial crossing of the mid-Atlantic ridge, occupies a position of genuine structural importance in the circulation of the deep Atlantic. It is, as earlier parts of this story have described, a gateway through which Antarctic bottom water must pass on its way northward, a choke point in the deep circulation that influences how heat and carbon are distributed across the Atlantic basin over timescales that matter to climate science. That a feature of this significance should remain as poorly studied as it has is not a reflection of scientific indifference. Exactly. It is a reflection of how the practical realities of doing science in difficult places interact with the institutional structures through which science is organised and funded. The Romanche is important enough to attract occasional expeditions. It has not yet been important enough, or accessible enough, or well understood enough to attract the kind of sustained, coordinated, multi-institutional effort that its significance arguably demands. And that gap between what the trench deserves in terms of scientific attention and what it has actually received is itself one of the more interesting things about the Romanche story. It raises questions that go beyond the trench itself, questions about how science decides where to look, how institutions balance the appeal of the unknown against the practical demands of producing results, and how the geography of knowledge, the uneven distribution of scientific attention across the surface of the planet and beneath its oceans, reflects not just the distribution of scientific importance, but the distribution of resources, proximity, and institutional momentum. The trench has not been entirely forgotten, and the story is not one of pure neglect. There are scientists who have dedicated significant parts of their careers to understanding what happens in the equatorial Atlantic, who have argued persistently for more attention to the Romanche, and who have produced careful, important work from the limited data available to them. Their efforts are what make it possible to say anything at all about the trench with confidence. But their work also makes clear, in its careful language of uncertainty and its honest acknowledgement of data gaps, just how much remains unknown. And it is that honest acknowledgement, that clear-eyed recognition of what has not yet been measured, sampled or observed, that sets the stage for the most recent chapter of the Romanche story. Because in the last decade or so, something has begun to shift. New expeditions have reached the trench, new instruments have been deployed, new data has begun to arrive. And what that data is starting to reveal about the Romanche and about what has been waiting in its depths is a story worth telling carefully. The shift has been gradual, and it would be misleading to describe it as a sudden rush of discovery. The Romanche has not become easy to reach. The currents have not calmed. The pressure has not relented, and the seismic restlessness along the transform fault has not paused to make things more convenient for visiting scientists. What has changed is a combination of factors that have been building slowly over the past decade or so, converging in a way that has allowed a small number of expeditions to return from the trench with something genuinely new to say. Better autonomous vehicles, more durable sensor packages, improved acoustic communication systems, and a growing awareness within the oceanographic community that the Romanche represents a gap in understanding that can no longer be politely deferred. These things have come together at roughly the same time, and the result, while still modest relative to the scale of what remains unknown, is the most detailed picture of the Romanche that science has ever produced. Some of the most significant recent work has focused not on the deepest parts of the trench itself, but on the water column above it and the sediment record preserved in its floor. Sediment cores, which are essentially long cylinders of compressed history pulled from the seafloor, have proven to be one of the more productive ways of learning something meaningful about the Romanche, without requiring instruments to survive in the most turbulent and geologically active zones. The sediment in and around the trench contains a record of what has been happening in the overlying water column for thousands of years, preserved in the shells of tiny organisms, in the chemistry of the particles that have settled slowly downward, and in the physical structure of the layers themselves. Reading that record requires patience and technical skill, but it does not require an instrument to sit undisturbed in a fast-moving current for months, which makes it considerably more achievable in a place like the Romanche. What those sediment cores have begun to reveal is a picture of variability that researchers suspected but could not previously confirm in detail. The flow of Antarctic bottom water through the trench has not been constant over geological time. There have been periods when the flow was stronger, periods when it was weaker, and shifts in the chemistry of the water that correspond to broader changes in the global climate system. Some of these shifts align with known episodes of glacial advance and retreat, which makes intuitive sense since the formation of Antarctic bottom water is closely tied to the processes of sea ice formation and deep convection around Antarctica. Processes that change significantly between glacial and interglacial periods. But the details preserved in the Romanche sediment record are more specific than a simple story of more flow during cold periods and less during warm ones. The chemistry suggests that the trench has acted as a kind of sensitive recorder of changes in the deep Atlantic circulation, capturing fluctuations that may not be visible in sediment records from other locations. In that sense, the Romanche floor is not just a passive repository of debris, it is something closer to an archive, and what is written in that archive is beginning to be read, carefully and with appropriate caution, for the first time. Water chemistry measurements from recent expeditions have added another layer to this picture. Scientists who have managed to collect water samples from within and near the trench have found evidence of the distinct chemical signature that Antarctic bottom water carries with it from its formation region around the Southern Ocean. This water is cold, dense, and rich in dissolved oxygen, qualities that distinguish it clearly from the older, warmer, more oxygen-depleted waters it displaces as it flows northward. Tracking these chemical properties through the Romanche has allowed researchers to confirm, with more precision than was previously possible, how the trench modifies the water as it passes through. The mixing that occurs inside the trench, driven by the turbulence and internal wave activity described in earlier parts of this story, does not simply blend the Antarctic bottom water with surrounding waters in a uniform way. The mixing is intense in some zones and relatively weak in others, and the pattern of where mixing happens and how vigorously it proceeds has implications for how much of the cold, oxygenated Antarctic water ultimately reaches the North Atlantic in a recognizable form. This is not a small detail. It bears directly on how the deep circulation of the Atlantic actually works, and on how well current oceanographic models capture that circulation. One of the more striking findings from recent water chemistry work is the degree to which the Romanche appears to generate what oceanographers sometimes describe as mixing hotspots, zones where the turbulent dissipation of energy is far higher than the surrounding ocean. These hotspots are not uniformly distributed through the trench. They tend to cluster in specific areas, apparently associated with particular features of the bottom topography, where the flow of Antarctic bottom water is forced to accelerate or change direction abruptly. The energy released in these zones drives mixing at rates that dwarf what happens in the open ocean around the trench, and that mixing has consequences for the temperature, salinity and density of the water that eventually exits the trench on its northward journey. Understanding where these hotspots are, how intense they are, and how they vary over time is important for building accurate models of deep Atlantic circulation. And until recently, the data needed to characterize them simply did not exist. Recent expeditions have provided a first approximation of where the most energetic mixing zones are located, though the coverage remains sparse and the picture is far from complete. On the biological side, recent work has been more limited, partly because biological sampling in the deep sea requires specialized equipment and careful handling, and partly because the logistical challenges of the Romanche have tended to push biology toward the back of the queue when expedition priorities are being set. But what has been collected, even in small quantities, has been enough to confirm that the trench supports life at its greatest depths, and that the life found there includes organisms that reflect the unusual conditions the Romanche offers. Microbial communities sampled from sediment cores have shown a diversity that researchers found somewhat unexpected, given the relatively low organic carbon input to a trench located far from productive coastal waters. The equatorial Atlantic is not a particularly rich ocean in biological terms. It does not receive the kind of nutrient upwelling that supports dense communities in other regions, and the deep Romanche is consequently not bathed in a rain of organic material the way some other deep trenches might be. Yet the microbial communities present in the sediment appear to be metabolically active, processing the limited organic material available and cycling nutrients in ways that contribute to the broader chemistry of the trench environment. What specific metabolic pathways dominate in the Romanche microbial community, and how those communities compare to those found in better studied deep trenches, remains an open question. There have also been limited observations of larger organisms in the water column above the trench floor, captured in the footage from remotely operated vehicles and the samples collected by trawl nets during expeditions that have approached the trench. These observations include the kinds of gelatinous zooplankton, small crustaceans and invertebrates that are common in the deep sea generally, but the taxonomic work needed to determine whether any of the Romanche specimens represent species distinct from those found elsewhere is still ongoing. Deep sea taxonomy is slow work at the best of times, requiring careful comparison of physical specimens under magnification, and increasingly genetic analysis to distinguish species that may look superficially similar but are reproductively isolated and evolutionarily distinct. The Romanche specimens collected in recent years are in various stages of this process, and it would be premature to make strong claims about endemism or uniqueness without the results of that analysis. What can be said is that the combination of cold Antarctic water flowing through an equatorial trench creates a set of environmental conditions that is genuinely unusual, and that unusual conditions have a tendency, over geological time, to produce unusual biology. Whether the Romanche has had time to develop a distinctly endemic fauna, and whether the periodic disturbances associated with its seismic activity and turbulent flow have disrupted any such development, are questions that remain genuinely open. Perhaps the most consequential recent finding, in terms of its implications for how scientists think about the trench, concerns the variability of the flow itself. Earlier understanding of Antarctic bottom water passage through the Romanche was based on relatively sparse measurements, and tended to treat the flow as something broadly steady, varying slowly in response to large-scale climate forcing, but not subject to rapid or dramatic fluctuations on shorter timescales. More recent observations, made possible by improved mooring technology and longer deployment periods, have complicated that picture considerably. The flow of Antarctic bottom water through the Romanche appears to be significantly more variable on timescales of days to months than earlier data suggested. There are episodes of intensified flow, apparently driven by fluctuations in the deep pressure gradient that forces the water northward, and episodes of reduced flow that may be associated with changes in the formation rate of Antarctic bottom water at its source. These shorter-term fluctuations have not been well captured in the models that oceanographers use to simulate deep Atlantic circulation, partly because the data needed to characterize them simply was not available until recently. Incorporating this variability into models is not a trivial exercise, but it is an important one, because the models that inform our understanding of how the deep Atlantic transports heat and carbon over decadal and longer timescales depend on accurately representing what happens at critical gateways like the Romanche. What makes all of this particularly interesting, and also somewhat humbling, is the gap between what these recent findings reveal and what they leave unresolved. Each new measurement, each sediment core, each water sample collected from the trench has answered some questions and generated several more. The picture that is emerging is not one of a well-understood system, with a few remaining details to be filled in. It's a picture of a complex dynamic environment whose behaviour is more variable, more spatially heterogeneous, and more biologically active than the sparse earlier data had suggested, and whose full characterization will require sustained observation over years, not a handful of expeditions spread across decades. The recent work has moved the Romanche from a state of near total obscurity to something more like a state of intriguing partial knowledge, which is in some ways a more uncomfortable place to be. When almost nothing is known, the gaps can be acknowledged and set aside. When enough is known to understand the significance of what remains unknown, the gaps become harder to ignore. There is also something worth noting about the way recent findings have been received within the scientific community. The results from Romanche expeditions over the past decade have attracted more attention than similar work would have a generation ago, partly because the broader context of deep ocean research has shifted. The deep sea is no longer treated as a remote and essentially static backdrop to the more dynamic processes of the surface ocean and atmosphere. It is increasingly recognised as an active participant in the Earth system, storing carbon, transporting heat, cycling nutrients, and harbouring biodiversity that we have barely begun to document. In that context, a poorly understood deep trench that serves as a critical gateway for deep Atlantic circulation is not an obscure curiosity. It is a missing piece in a puzzle that scientists are actively trying to assemble, and the recent findings from the Romanche have helped to make that case in concrete, measurable terms. This does not mean that the barriers described in earlier parts of this story have disappeared. The Romanche is still remote, expeditions are still expensive, equipment is still lost, the currents are still unpredictable, the seismic risk is still real, the funding landscape is still competitive, and the logistical challenges of mounting a sustained observing program in the equatorial Atlantic have not been solved by a handful of successful deployments. What has changed is the scientific case for doing so, which is now stronger and more specific than it has ever been. Researchers who advocate for more sustained attention to the Romanche can now point to concrete findings that illustrate what the trench can reveal, and to concrete gaps that illustrate what remains to be learned. That is a more persuasive argument than a general appeal to the importance of deep ocean research, and it has begun to move the needle slowly in the direction of greater institutional commitment. The gap between what scientists suspect is happening in the Romanche and what has actually been confirmed remains substantial. There are hypotheses about the biological communities in the deepest zones that have not been tested, because no instrument has yet reached those zones and returned with usable data. There are questions about the long-term trend in Antarctic bottom water flow through the trench, and whether that flow is changing in response to the warming and freshening of source waters around Antarctica, that cannot yet be answered with confidence because the observational record is too short. There are questions about the geological history of the trench, about how its topography has changed over millions of years, and how those changes have affected the circulation and biology of the deep Atlantic, that will require a combination of seismic surveys, sediment coring, and careful modelling to address. And there are almost certainly questions that have not yet been formulated, because the data needed to even recognise that they are questions has not yet been collected. That is, in a sense, where the Romanche stands today. Not entirely unknown, but far from understood. Not entirely avoided, but still approached with caution and humility by the scientists who know it best. A place that has begun to yield its secrets in small, carefully extracted fragments, while making clear that the larger secret, the full picture of what the trench does, what it contains, and what it has to teach about the deep ocean and the climate system it helps to regulate, remains stubbornly beyond reach. And that tension between what recent expeditions have managed to find and what those findings reveal about the scale of what is still missing is precisely what makes the Romanche one of the more compelling unfinished stories in contemporary oceanography. Not because of mystery for its own sake, but because the specific things that remain unknown about this specific place happen to matter in ways that extend far beyond the trench itself, into questions about the ocean's role in the climate, and about how well we actually understand the deep systems that keep the planet's chemistry in balance. That is the thread that the next part of this story will follow. There is a particular kind of importance that is easy to overlook, and it tends to belong to things that are neither famous nor visible. A valve in a pipe, a junction in a circuit, a narrow mountain pass that most travellers never think about because they have never needed to cross it. The Romanche Trench belongs to this category, and perhaps that is part of why it has remained under study for so long. It does not announce its significance. It sits at the bottom of the equatorial Atlantic, dark and cold and largely silent, doing something that matters enormously to the functioning of the planet's climate system without attracting the kind of attention that would normally follow from something that important. To understand why the Romanche matters in ways that extend well beyond scientific curiosity, it helps to think for a moment about what the deep ocean actually does. The ocean is not simply a large body of water that sits between the continents and occasionally produces storms. It is one of the primary regulators of Earth's climate, and it carries out that regulation through a set of interconnected processes that move heat, carbon, oxygen, and nutrients around the planet over timescales ranging from years to centuries to millennia. Near the surface, wind and solar heating drive circulation that most people are at least vaguely familiar with. The Gulf Stream carries warm water northward along the eastern coast of North America. Trade winds drive equatorial currents. Seasonal patterns shift the position of warm and cold water masses in ways that influence rainfall and temperature across entire continents. These surface processes are relatively well understood, at least in their broad outlines, because they are accessible enough to study. But beneath the surface, particularly in the deep ocean below about 1,000 meters, a slower and less visible circulation operates. This is sometimes called the thermohaline circulation, or more informally the global ocean conveyor belt, and it is driven not by wind but by differences in temperature and salinity between water masses. Cold, dense, salty water sinks in certain high-latitude regions, most importantly around Antarctica and in the North Atlantic, and then spreads slowly across the ocean floor, eventually rising again in other parts of the world as it warms and becomes less dense. This deep circulation is slow by the standards of surface currents. Water that sinks near Antarctica today may not resurface for centuries, but what it lacks in speed it more than compensates for in scale and consequence. The deep circulation moves enormous quantities of heat from the tropics toward the poles, moderating the temperature of regions that would otherwise be far colder. It carries dissolved oxygen into the deep ocean, sustaining the ecosystems that live there. And critically, it moves carbon dioxide, absorbing it from the atmosphere in regions where water sinks and gradually releasing it elsewhere, in a process that plays a significant role in regulating the concentration of carbon dioxide in the atmosphere over long time scales. The Romanche Trench sits directly in the path of one of the most important components of this deep circulation. Antarctic bottom water, which forms around the edges of Antarctica as extremely cold, dense water sinks to the ocean floor, spreads northward along the floor of the Atlantic. When it reaches the equatorial Atlantic, it encounters a significant obstacle. The mid-Atlantic ridge, which rises thousands of meters above the surrounding ocean floor and effectively divides the deep Atlantic into eastern and western basins. The Romanche Trench, along with a small number of other deep fracture zones, provides the only pathway through which Antarctic bottom water can cross from the western basin into the eastern basin. Without these passages, the deep eastern Atlantic would effectively be cut off from the source of its coldest, densest water. With them, the circulation continues, the deep water is renewed, and the eastern basin remains connected to the broader global circulation. This makes the Romanche not merely an interesting geological feature, but a genuine control point in the deep Atlantic circulation system. The rate at which water flows through the trench, the temperature and salinity of that water as it passes through, the mixing that occurs as it interacts with the complex topography of the trench itself, all of these factors influence the state of the deep eastern Atlantic downstream. And the state of the deep eastern Atlantic influences in turn the broader Atlantic circulation, which influences heat transport, carbon storage, and ultimately the climate of the surrounding continents. It is a chain of consequences that begins in one of the least visited places on Earth and ends in patterns of temperature and rainfall that affect hundreds of millions of people. What makes this particularly relevant in the present moment is that the deep Atlantic circulation is changing. There is now substantial evidence gathered from a combination of direct measurements, satellite observations, and paleoclimate records that the broader Atlantic overturning circulation has weakened over recent decades, and that this weakening is connected to the warming and freshening of water masses around Antarctica and in the North Atlantic. The source waters that feed the deep circulation are being modified by climate change, and those modifications propagate through the system over time. What happens at critical gateways like the Romanche? How much water passes through? How that water has been modified by mixing within the trench, whether the flow is accelerating, decelerating, or becoming more variable, is directly relevant to understanding how the deep circulation is responding to these changes and what the consequences might be for the climate over the coming decades and centuries. The problem is that the observational record for the Romanche is far too sparse to answer these questions with confidence. A few measurements collected over a span of decades, separated by long gaps and varying in methodology, cannot establish the kind of baseline that would allow scientists to detect trends or attribute changes to specific causes. To know whether the flow through the Romanche is changing, you first need to know what it looked like when it was not changing, and that requires sustained, consistent observation over time. That is precisely what the trench has never had. Each expedition has provided a snapshot. What is needed is a continuous record, and the barriers to establishing one, the remoteness, the equipment losses, the unpredictable currents, the seismic risk, the cost, all of the challenges described in the earlier parts of this story have so far prevented that record from being built. This is not a purely academic frustration. The deep Atlantic circulation is one of the components of the Earth system that climate models have the most difficulty representing accurately, partly because the observations needed to validate and constrain those models are incomplete. When oceanographers build numerical models of the Atlantic circulation, they must make assumptions about what happens at places like the Romanche, how much mixing occurs, how the flow is distributed across the trench's complex topography, how the behaviour of the trench changes in response to upstream conditions. Those assumptions are informed by the limited observations that exist, but they cannot be thoroughly tested against reality, because reality in this particular location has not been measured in sufficient detail. The result is a source of uncertainty in the models, and that uncertainty propagates into projections of how the circulation will evolve under different climate scenarios, and into projections of what that evolution will mean for regional climate, sea level, and the ocean's capacity to absorb carbon dioxide from the atmosphere. There is something almost ironic about this situation. The Romanche Trench is avoided in part because it is difficult and expensive to study, but it is also a place that, if properly studied, could reduce uncertainty in the very climate models that policymakers and scientists rely on to understand the risks of a warming world. The cost of not studying it is not simply a gap in scientific knowledge for its own sake. It is a gap in the information that feeds into decisions about energy, infrastructure, and the management of climate risk. Framed that way, the institutional reluctance to invest in sustained observation of the Romanche looks rather different than it might at first. It is not simply a matter of scientific priority. It is a question about what kinds of knowledge gaps are acceptable to carry forward and which ones are too consequential to leave unaddressed. The growing recognition of this within the oceanographic community has begun to shift the conversation around the trench. There is now a clearer articulation in the scientific literature and in discussions at major oceanographic conferences of the specific reasons why the Romanche matters for climate science, and of the specific observational gaps that need to be filled. This is a relatively recent development, and it reflects both the maturation of deep ocean research as a field and the increasing urgency of questions about how the ocean is responding to climate change. A decade ago, the argument for studying the Romanche more intensively was largely one of general scientific completeness. The trench is an important feature that we know too little about. today, the argument is more specific and more pressing, because the things we do not know about the Romanche are things that directly affect our ability to project the future behaviour of the Atlantic circulation and the climate it helps to regulate. This shift in framing has begun to attract a different kind of attention to the trench, not just from physical oceanographers interested in deep circulation, but from climate scientists, biogeochemists interested in the ocean's carbon cycle, and modellers looking for the observational constraints they need to improve their representations of the deep Atlantic. The Romanche is increasingly appearing in discussions about where sustained ocean observing systems should be expanded, and about which gaps in the existing observational network are most consequential for climate science. It has not yet achieved the level of institutional commitment that some other critical ocean passages have received, but the scientific case for that commitment is stronger now than it has ever been. There is also a growing awareness that the Romanche is not merely a passive conduit for Antarctic bottom water, but an active site of mixing and transformation that alters the properties of the water as it passes through. The turbulence generated by the trench's complex topography, the internal waves that propagate through the water column, the interaction between the deep flow and the rough walls of the fracture zone, all of these processes modify the temperature, salinity, and density of the water in ways that matter for what happens to it downstream. Understanding those modifications requires not just measuring the water entering and leaving the trench, but understanding the dynamics of what happens inside it, which is precisely the kind of detailed, sustained observation that has been most difficult to achieve given the practical barriers to working in this environment. One way to think about the significance of this is through the lens of what oceanographers call water mass transformation. When Antarctic bottom water enters the Romanche Trench, it is extremely cold and dense. When it exits on the other side, it has been mixed with overlying water masses and its properties have changed. That mixing is not random or uniform. It depends on the specific topography of the trench, the intensity of the turbulence at different locations within it, and the structure of the incoming flow. If scientists do not understand those mixing processes in sufficient detail, they cannot accurately represent them in models, and if the models do not accurately represent them, the downstream properties of the water are wrong, and the errors propagate through the model's representation of the entire deep eastern Atlantic. It is the kind of problem that seems technical and specialised until you follow the chain of consequences far enough to see where it ends up. What makes the Romanche particularly interesting in this context is that it may not behave the same way under all conditions. There is some evidence from recent observations that the flow through the trench is not steady, that it varies on timescales from days to years in response to changes in the upstream conditions and in the broader circulation. If the flow is variable in ways that current observations cannot fully characterise, then the long-term averages derived from sparse measurements may not accurately represent the typical state of the system, let alone its current trajectory. This is another way in which the sparseness of the observational record is not simply a gap in knowledge, but a potential source of systematic error in how the trench's role in the circulation is understood and modelled. The tension between knowing that the Romanche matters and being unable to study it with the consistency that its importance demands is one of the more quietly frustrating situations in contemporary oceanography. The scientists who work in this field are not unaware of the gap. They are, in many cases, acutely aware of it, and they have been making the case for more sustained attention to the trench for years. But the practical barriers are real, and the competition for funding and ship time in a field where resources are always constrained means that even a compelling scientific argument does not automatically translate into the observations needed to address it. Progress has been made, as the recent expeditions described earlier in this story illustrate. But the pace of progress remains slow relative to the scale of what is unknown, and relative to the urgency of the questions that the Romanche's behaviour bears upon. There is also something worth saying about what it means for climate science to have a critical junction in the deep ocean circulation that is so poorly characterised. Climate models are built from the best available data, and they are tested against observations wherever observations exist. But in the deep ocean, and particularly in places like the Romanche, the observations are thin enough that models can produce results that look plausible in the aggregate, while being wrong in ways that are difficult to detect. A model that represents the Romanche as a simple, steady conduit, when it is in fact a complex variable and highly turbulent mixing zone, will produce a deep Atlantic circulation that looks broadly reasonable, but carries errors that accumulate over the long time scales of deep circulation. Those errors are not necessarily visible in the short-term comparisons that are typically used to validate models, but they can matter for projections of how the system will evolve over decades and centuries. This is not a hypothetical concern. It is a recognized source of uncertainty in deep Atlantic modelling, and the Romanche is one of the places where reducing that uncertainty requires observations that do not yet exist in sufficient quantity or quality. What the Romanche represents, then, is something more than an unvisited corner of the ocean floor. It is a place where the practical limits of human exploration intersect with the practical limits of climate science, and where those two sets of limits reinforce each other in ways that have real consequences for how well we understand the system we are depending on to regulate the planet's climate. The barriers to studying it are not simply technical inconveniences. They are obstacles to a form of knowledge that matters, and the cost of those obstacles is not borne only by the scientists who would like to work there, but by the broader project of understanding how the deep ocean is changing and what that change means for the world above it. That is a weight that sits quietly beneath the surface of the Romanche story, and it becomes harder to ignore the more carefully you look at what the trench actually does and why it does it. The question of what lies beyond the current limits of observation there, and what it would take to reach it, is one that the final part of this story will settle with, and so we arrive, finally, at the place where the explanation runs out. Not because there is nothing left to say, but because the Romanche Trench has a way of returning you to the same quiet threshold, no matter how many facts you gather, no matter how carefully you trace the current, or measure the pressure or reconstruct the flow from instruments that survived long enough to tell their story. You come back eventually to the simple and slightly humbling recognition that the ocean floor down there is still, in most of the ways that matter, its own. There is something worth sitting within that. We live in a moment when the phrase unexplored territory has become almost nostalgic, something that belongs to old maps with sea monsters drawn in the margins, to accounts written by sailors who had no way of knowing what lay beyond the next headland. The world above the surface has been photographed from orbit, measured by satellite, traced to the last road and rooftop. Even the most remote places on land carry the faint fingerprint of human attention. But the deep ocean does not. The Romanche Trench, sitting along the equatorial Atlantic, crossed by shipping lanes, flanked by continents that have been inhabited for thousands of years, is still, in its deepest and most turbulent interior, largely unknown. Not in the way that a library book is unknown when it sits unread on a shelf, waiting. In the way that a room is unknown when the door has not yet been built. What the Romanche represents, in the end, is a particular kind of frontier. Not the dramatic kind that announces itself with spectacle, not the frontier of space with its cold distances and visible darkness, not the frontier of a mountain that at least offers you a summit to aim for. The Romanche is a frontier of patience and pressure and cost. A frontier defined not by what lies beyond the horizon, but by what lies below a surface that looks, from any ship crossing it, entirely unremarkable. The equatorial Atlantic on a calm day is just water. Blue, warm at the surface, glittering in the sun. You would have no way of knowing, looking at it, that 6,000 meters below the keel, a narrow canyon cuts through the floor of the ocean and channels some of the coldest water on Earth from one basin to another in a turbulent, poorly understood and genuinely consequential flow. The ocean keeps that information to itself with complete indifference. That indifference is part of what makes the Romanche story feel different from other stories of exploration. Most exploration narratives have an element of confrontation in them, a sense that the environment resisted and the explorer persisted, that there was something almost dramatic about the encounter between human ambition and the world's difficulty. The Romanche does not offer that kind of drama. It does not resist in a theatrical way. It simply exists at a depth and in conditions that make sustained observation extraordinarily difficult, and it waits, as it has waited for the entire history of human curiosity, for someone to find a way to reach it properly. The instruments that have been lost there were not defeated by anything that felt like opposition. They were defeated by physics, by pressure and turbulence, and the sheer mechanical difficulty of holding equipment in place in a flow that does not accommodate it. There is no drama in that, only difficulty, and difficulty of a kind that does not resolve itself by trying harder. What it resolves itself by, if it resolves at all, is time and ingenuity, and the slow accumulation of better tools. The history of deep ocean science is in many ways the history of learning to build things that can survive conditions that destroy everything built to a lesser standard, and then learning from what those things report back before they fail, and then building something better. That process has been underway for the Romanche, as the more recent expeditions have shown, and it will continue. The gaps are large, but they are not permanent. They are the gaps of a field that has not yet had the resources or the technology to close them, not the gaps of a place that is fundamentally unknowable. But there is a difference between unknowable and unknown, and the Romanche for now sits firmly in the second category. What is there in the sections of the trench that have not been surveyed, in the biological communities that have not been sampled, in the sediment layers that have not been cored, in the turbulent mixing zones that have not been instrumented, is not nothing. It is almost certainly something, and in some cases probably something, that would matter to the questions scientists are already asking about the deep ocean and its role in the climate system. The organisms living in those conditions adapted to the intersection of Antarctic cold and equatorial location, to the particular chemistry of water that has travelled from the Southern Ocean and been modified on its way through the trench, to the seismic activity of a transformed fault zone that periodically reshapes the environment they inhabit. Those organisms represent a biology that has not been described. The sediments on the floor of the trench carry a record of how the flow through it has changed over geological time, a record that could help scientists understand how sensitive the deep Atlantic circulation is to the kinds of changes that are happening now at the surface. All of that is there, waiting in the dark, at a depth that most instruments do not survive, and in conditions that most research programs cannot afford to address properly. There is a kind of quiet melancholy in that, if you let yourself feel it. Not the melancholy of loss, because nothing has been lost that was ever held. More the melancholy of distance, of knowing that something significant exists and being unable to reach it, not because of a lack of desire, but because of a gap between what the question requires and what the available tools can provide. Scientists who work on the deep Atlantic circulation carry that gap with them. It shows up in the uncertainty ranges of their models, in the caveats of their papers, in the conversations at conferences where someone raises the Romanche and everyone in the room nods with the particular expression of people who know exactly what the problem is and do not yet have a solution for it. And yet, and this is worth saying clearly, the work continues. The expeditions that have reached the trench in recent years, the instruments that have survived long enough to return data, the sediment cores that have been recovered, the microbial samples that have been analysed, all of that represents real progress. It is slower than the importance of the questions would seem to demand, but it is genuine and it is cumulative. Each deployment, even the ones that fail, teaches the engineers and scientists something about what the trench requires of its instruments. Each successful recovery adds a piece to a picture that is still mostly missing but is no longer entirely blank. The trajectory, if you stand back far enough to see it, is toward more knowledge, not less. The Romanche is not retreating from human understanding. It is simply taking its time. There is something almost fitting about that, given where the trench sits and what it does. The water that flows through it has been travelling for centuries, moving in slow, cold, dense currents from the Southern Ocean northward along the floor of the Atlantic. patient in a way that has nothing to do with intention and everything to do with physics. The Romanche is a waypoint in that long journey, a place where the water is squeezed through a narrow passage and mixed and modified before it continues on its way into the eastern Atlantic basin. The timescale of that circulation, the centuries it takes for a parcel of water to complete its deep journey, is so far outside ordinary human experience that it is almost impossible to hold in mind. And yet it is real, and it matters, and the Romanche is part of it in a way that the ocean does not explain or announce. It simply does it, continuously, regardless of whether anyone is watching. Perhaps that is the most honest way to leave the story, not with a resolution, because there is not one yet, and not with a promise that the remaining mysteries will soon be solved, because that would be overstating what the current trajectory of research can guarantee. But with the recognition that the Romanche Trench is one of those places that does its work quietly and completely, without any reference to the human desire to understand it. The deep current passes through. The water is mixed. The properties of the eastern Atlantic are shaped by what happens in that narrow canyon. The biology persists in conditions that would end most things. The sediment accumulates, layer by layer, carrying its record of how the flow has changed. All of this happens whether or not a mooring is anchored there, whether or not a lander has made it to the floor, whether or not a ship is on the surface above it taking measurements. That independence is not a rebuke. It is just the nature of the place. The ocean does not require our attention to function, and the Romanche does not require our understanding to do what it has always done. But we require the understanding, or at least we will, as the climate system continues to change, and the deep circulation that the Romanche helps to shape becomes more important to predict and monitor. The urgency is not in the trench, it is in us, in the models that carry its uncertainty forward into projections of how the ocean will behave in a warmer world, in the gap between what those models assume and what the trench actually does. That is a gap worth closing. And if the history of ocean science is any guide, it will be closed slowly and imperfectly, and at considerable cost, by people who are willing to send instruments into conditions that destroy them, and to learn from what comes back before it fails. That is not a romantic story exactly. It is more of a practical one, a story about persistence and engineering and the willingness to work in the margins of what is currently possible. But it is a real story, and it is still being written, and the Romanche is still at the centre of it, 6,000 metres below the equatorial Atlantic, doing what it has always done. If you have spent this time following the trench from its discovery to its present obscurity, through its physics and its biology and its geological instability and its role in the deep circulation, you may have noticed that it never quite becomes dramatic. There is no single moment of revelation, no discovery that changes everything, no expedition that finally cracks it open. There is only the slow accumulation of partial knowledge against a background of genuine difficulty, and the growing recognition that the partial knowledge matters more than it might first appear. That is, in some ways, a more accurate portrait of how ocean science actually works than the dramatic version would be. The ocean is large and deep and mostly dark, and understanding it is a long, patient, expensive, often frustrating project that rewards persistence more than spectacle. The Romanche is a small part of that project, in the sense that it is one feature among many in a global ocean that has thousands of features that are poorly understood. But it is not a trivial part. The water that passes through it connects the Southern Ocean to the deep Eastern Atlantic in a way that nothing else does at that latitude, and the mixing that happens inside it shapes the properties of that water in ways that propagate through the circulation for centuries. That is not a small thing to leave uncharacterized. It is the kind of thing that, once you understand what it does, you wish you had been paying closer attention to all along. And so the trench sits there, as it has sat for millions of years, cut into the floor of the Atlantic along the line of a transform fault that still moves, still generates earthquakes, still reshapes the terrain on timescales that make human attention look brief. The cold water still passes through it. The organisms still live in it, adapted to conditions that science has barely begun to describe. The sediment still accumulates. The turbulence still destroys instruments and mixes water masses and confounds the models that try to represent it. And somewhere on the surface, a ship is probably planning a return, loading instruments that have been redesigned to survive a little longer, carrying scientists who have read the previous failures carefully and believe they have found a way to do better this time. That is where the story of the Romanche actually lives, not in the dramatic depths, not in the mystery of what might be down there, but in the quiet, ongoing effort to close the gap between what the trench does and what we understand about it. It is a slow story and an incomplete one, and it will remain incomplete for a long time, but it is moving in its patient way towards something. And the ocean, as always, is not in any particular hurry to meet us halfway. Wherever you're listening from tonight, whatever the hour, whatever the temperature outside your window, you are somewhere near the surface of a planet that is mostly water, most of which is deep and cold and dark and still largely unknown. The Romanche is just one place in that darkness, one passage in a system so large that a lifetime of research barely scratches its edges. But it is a place that matters, and knowing that it matters, even without being able to reach it fully, is its own kind of understanding. Sleep well.